And we're live.
All right, cool.
Hey everyone, how's it going? I just wanted to give a quick introduction to our AP Physics team and kind of go over how the stream will work really quick. So right now you have Peter Apps, our AP Physics CRAM teacher, and then Christian Horner, who has been streaming for AP Physics for us as well. Um, in terms of the stream structure, we'll be doing full content review, then we'll take a quick break, 5-10 minutes, and then Peter will be hosting the FRQ section of the stream. We're disabling the chat for the beginning of the stream just to go over general exam stuff, things that you should know to make sure you don't have any technical issues, and you can avoid all of those mishaps that people have been having. So I'm gonna let Christian Horner just take the stream off, and then we'll see you in a bit.
All right, cool. Thank you. All right, so here's the thing that I'd like for you to know. Your ticket will be valid for May 14th, which is tomorrow, and have you sign in, make sure you sign in about 30 minutes early. You need to be in about 3 p.m. If you're not in at 3:30, you want to try to get in as soon as you can, because if you don't, and you have trouble getting in, once the test starts, then you've got to be in. So you won't be able to get in after that. So just be real careful with that, and I think you'll be okay. All right, so next slide. This one, what to expect on this year's exam. It's not going to be any more difficult to earn a 3, 4, or 5. Even if the exam question seems like it's a little hard, it's okay. That's the way they designed it. The test is that way every single year. I get the privilege of going to Kansas City every year. This year we're going to do it at home, but I'm one of the readers. I'm the one that will look at one of the questions on your exams and grade it. So we grade it anywhere between 5 and 12,000 of the same question as we go through.
Hey Christian, your sound is a little choppy. Can you check that out?
Yeah.
Sorry to interrupt, but it's really hard to hear.
No, you're good. Are you getting an
echo? It kind of like goes in and out.
Oh, it just goes in and out. Okay, let's see. We'll fix this. That a little bit better?
Can you talk a little bit?
Yeah, I'll just keep going. Just stop me. AP exams, remember, they're never graded on a curve, and this one's not going to be any bit different. So you're not competing against anybody else. You're really just going to be with yourself. And so the thing that you need to know is this. They have a set score. So if this year, let's say it's out of 100 points, they've already said that 58 out of 100 points would be a 3. They say that somewhere in the 65, 67% would be a 4, 78% or so would be a 5. They do kind of shift that a little bit. They use some really impressive statistics to do that, and then they're going to make sure that it kind of meets the norms that they have. But you shouldn't have any harder of an exam. In fact, I'm hoping that because there's only 2 questions and that you really don't have those last 2 sections on waves and on electricity, that you should do really well. Don't worry if you don't complete all parts of the questions too. You don't have to do the entire question to get a 5. So remember, traditionally it's been somewhere in the upper 70% is a 5. And so if you don't get all the way done, that's okay. The test was designed, you know, that you have 25 minutes for the first question, you have 15 minutes to answer the second question, and you have a 5-minute time that you have to upload. When that time starts, you need to upload immediately. Don't wait. We've had some students already that are at my school. I know that waited until the last second and they didn't get the question answered and uploaded. And you don't want to have to take the test again in June. So anyway, just kind of a word of warning. Speaking of what you need to do, this year there are 3 ways to submit your responses. The first way is the way that I 100% highly recommend. I've talked to both the AP Physics C person who is in charge of creating an AP Physics C test. Her name is Michelle Strand. She's in North Dakota, and she's in charge of all the AP Physics C exams. Othar Strotterman is from Kansas City, Kansas City, Missouri, and he teaches there and is in charge of all the AP Physics 2. They've seen all of the exams, including the AP Physics 1 exam, and they tell me there's absolutely no reason for you to do anything but type, copy, and paste that typed response. The other thing you need to know is use Google Chrome for sure. If you can't, for whatever reason, please use Safari, Firefox, or Edge. Do not use Internet Explorer, it won't work. The other thing you want to be careful of is make sure that you turn off the program called, and I'm going to look it up here, Grammarly. That's right. So please don't use Grammarly. You're going to find out that is a program that won't work really well. Here is the best way to submit. If you do it any other way, there are a lot of glitches with the other ways. You can type in Google Docs, Microsoft Word, Notes, or any other application like that. You'll probably, well, not probably, really want to make sure you put your API and your initials at the top. So you should already have your questions, and you should be good there. You still having trouble? Oop, go ahead and pop your mic back on. Your mic is off. Sorry. Oh, still off. Ah, that's really weird. Okay, so we're going to just keep going here. I'm going to switch mics, I think, and that should help a little bit. Sorry about this, folks. Let's see if I can do this really quick. Here we go. All right, hold on just a second. We'll get you. I see what it is. Okay, you should be able to hear me a lot better now. Hopefully that works better. Okay, sorry about that, folks. And let's see if that's better. Okay, hopefully that's a little bit better. Why don't we enable the chat for just a second and see if maybe this is, well, you know what? We won't, because I think you're left. All right, let's just go back to this and make sure that you're good here. So go ahead and you'll want to make sure that you are using any of these approved web browsers, and just make sure that everything works. There is a site that you can go into and kind of check everything. That's super important if you want to do it. The second way to do it is to attach a document. For some of my students, I have one student in particular that had a lot of trouble with uploading. It tells you that it can't upload. So you want to definitely check it. The third way is to take pictures. I would highly recommend you don't do that. That comes from the people that are at the AP Physics. They wrote all the questions and things. We've kind of learned from that AP Physics C test that it's probably a tough thing to do. So you do not want to probably do it that way. All right, let's go ahead and talk a little bit about something a little bit different. So we need to talk about how to actually get really great points on the AP Physics exam. So the best way to get points on the exam is for you to write your paragraph length response. Remember, this is the second question. There's two questions. First question is a qualitative, quantitative analysis. The second question is a paragraph length response. There are four letters you need to know. You already know them. It's A, B, C, and D. So A just means answer the question. And please make sure you answer the question. If you don't answer the question, then the rest of what you've written is kind of difficult to understand. Uh, B is probably the most important thing. Tell us about the basic physics or the basic principles or the basic equation. So start with physics principle, law of physics, some sort of physics equation, and give us kind of why that is related. So how do you do that? You're going to use citing evidence. So that means that you're going to talk more than just about physics. You're going to tell about the situation that you have. So, for example, if it's a ball on an incline, you're going to want to tell what is that ball doing? Is it rolling down the incline? Is it rolling up the incline? Is there somebody throwing that ball? And then finally, you want to make sure that you draw all of this together. So once you've said all your basic physics out and you've cited your evidence, make those link together, because I think that's the important thing. Now, here's the thing that we've talked about a lot just with my students and with some other students, some other things, and it is to use the BCDA format. So you can do ABCD, but you tend to forget your basic physics, and we really want to make sure that you include that basic physics. So basic physics, then cite evidence, then draw it together and answer the question. You can do D and A uh, in the same sentence. So you should have about 3 sentences for each one of these paragraph responses. Typically, you'll have 4 to 6 of them, and that is probably one of the easier ways to do it. We're going to go through some of those, and so what we'll do is I'm going to get out of this. We're going to go and start talking about kinematics, and let's see if we can get this to work out really well. All right, we're going to use a program tonight called Pear Deck. Pear Deck is why we have the chat turned off. So you can ask questions using Pear Deck, but more importantly, you're going to be able to actually ask some questions using Pear Deck. So I'm going to start this. Some of you have used Pear Deck before. Probably a lot of you have not. This is a pretty easy program to use. If you are on a cell phone right now, what you can do is go ahead and you can go to joinpd.com and then type in the code. If you are on a computer, I would just go up and open another tab. So for example, I just kind of clicked on a tab there, but you can just open another tab. And once you open that tab, you'll be able to go in and you will see the question as well as your response. This is very anonymous, which means that I'm going to actually show some of the responses. And those responses, when you see them, will come up and when you see the responses, we'll talk about which ones are correct and which ones probably are not. So what I would love for you to do is go ahead and do that. We'll give you a little bit of time here. It can actually take a lot of students. So you can hop onto this and we shouldn't crash it, but we'll see. You guys are doing a phenomenal job of doing that. I'm going to open another window. This window helps me see your responses. If at any time you do have a question and you want to, you can go ahead and type that question. But please realize with the number of students that we have today that that's going to be a little bit difficult to do. So we'll do the best we can at trying to take a look at some of your questions and see what you have. Hopefully you were here at the very beginning when we were talking about how to submit your response. The physics teachers that have given the AP Physics C exam, I'm one of those, we have decided after that, definitely instead of uploading or taking pictures, neither of which you need to do, you'll want to type in a Google Doc or in a Word doc or Pages doc and then copy that and paste it. If you can copy and paste those things, you will be 100% set. All right, so it looks like we're kind of stuck here at about 526 students or so. We're getting a little bit bigger. What I'm going to do is go ahead and start this. And what I'll also do, I think, well, I can't change anything there. Okay, yeah, I'll be able to do that either. All right, so I think suddenly I got it. Okay, cool. So now I see what I can do. All right, awesome. So okay, Mike is cutting in and out, is that right? Okay, so let's try
Hey, Christian. Can you do a mic check? And make sure you toggle your mic back on because nobody can hear you. Sorry about this, guys. We'll be with you in just a second. We're just trying to make sure his mic is settled. So he's just taking a moment to restart, I believe. So just give us 1 minute. Everybody take a deep breath. We'll be back. Don't worry about this.
Breathe, y'all. What up, AP Physics?
It's Amanda, the founder.
I'm just here to give you a full Amanda pep talk. If you haven't had one yet, I don't know. I know you're super stressed out, and just X out of his. You can't close it.
Yeah, I can't.
All right. So I know you're super stressed out. I know that physics is tomorrow. It's gonna be okay. And I know that it's gonna be okay because you're here right now. You're putting in the work. All right. So we're having a little bit of technical issues because, you know, technology, but we're going to figure this out. So wherever you are, just say it out loud. I got this. Maybe that will help.
How's it going on your end, Christian?
Can you turn the chat back on?
All right, turning the chat back on, guys. Relax, please. We'll get through this.
I'm curious, like, you know, I know it's sort of just like, it is what it is, you know? But like at the end of the day, like, we're here for 5 hours. You know how long 5 hours is? It's a really long time. And so we will cover everything. So I know that you're freaking out because we're like, oh, we're wasting time. I need to be studying. But like, it's been 20 minutes. We'll be live for 5 hours. Christian is such a good AP physics teacher. Like, I don't know physics. Like, I'm a history teacher. But if I stayed in this chat, even though I have not taken this class at all, I would probably get, I don't know, 2 or 3 tomorrow. And like, I don't know physics, and he could help me. All right. So I know that like, I know the panic is real, but we are not going to let you. Okay.
Okay. Can you hear me now?
All right. You sound perfect,
Woo!
Christian.
Woo!
Just to reiterate, Christian is one of the best physics teachers out there, and he's a very veteran AP reader. So make sure you listen to everything that he has.
Can't hear you at all.
No.
All right, you guys got this. You don't need any more pep talks from me. You got this.
I'm gonna hop off. These students are waiting for you. So
all right,
let's just do this.
Bye, y'all.
Bye.
Close our
All right. Now I should be back. Okay. So I should be back. I think you guys can hear me now. All right, cool. So it looks like you guys are on and typing on the Pear Deck, which is awesome. Okay, good. Woo! All right. Yay! Bad. I don't know why this is happening, but this is just one of those technical things. All right, here we go. Okay, distance versus displacement. We want to know if you start at G and move to A, and then what is your distance? If you move from A to F to C, how far did you go? So we're looking for distance. And we have a lot of great responses so far that I see. They look really, really, really good. And those responses are awesome. So let's take a look at the answer. So the answer to this one, in just a second, because there's 9 million of you here. Let's back up one. We'll give it a second. Yeah, so here we go. Here are our answers. You should have chosen from G to A. So if I go from G to A, it is 17. Notice there's not a positive. There is not a negative on that. So for distance, distance is a scalar. So there is absolutely no positive or negative on it. We just say how far you went. All right, awesome. Let's do the next one. So this next one is displacement. We want to know, what is the displacement? So displacement is a vector, which means that you've got to go in and you've got to find out what is the direction. So what is the direction? What is the direction? All right, here we go. So I'm starting to see some good answers here. So remember, we want displacement, not distance. We want it for G to A, and then we want it from A to F, and then to C. And so if you're on Pear Deck, you can go ahead and type your answer. So I'm looking like some good answers here. Some of these answers are looking good. You guys are rock stars. I love it. It's phenomenal. Very nice. And then we want to go from A to F to C. All right, time's up. Let's take a look. So here we go. We'll give it a second to catch up since there's so many people. And I think, there we go. So it is negative 17 this time. Why is it negative? Remember, it's negative because it is displacement. And so that's a scalar. Scalars have to have a direction. So we're going to start at G and go all the way over to A. For A to F to C, and that's really just going from A to C. Because remember, for displacement, it's where you start and where you stop. You don't worry about the path. So we started at A, we went all the way to F and then back to C. But if you looked at where they started and where they finished, they started at A, they went to C, and that distance, that displacement is positive 5. So this one is definitely a vector, and distance is a scalar. All right, let's go ahead and check on the next thing. So we'll give it a second to come up. Here it comes. Do, 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 do. And all right, here we go. Let's practice. This track is 100 meters from start to stop. And you know what we're going to have to do? I think what we're going to have to do, there we go. I want you to tell me, I would love for you to tell me, what is the distance around the track? And then next, what is the displacement around the track? So we want the distance around the track, And then we want the displacement around the track. And this is probably the last one we're going to do using. This is the last one we're going to use using Pear Deck because it's just slowing us down. In fact, I think it's crashed on us. All right, cool. So we will just go the regular way. And that is to use just our regular old guy right here. So this will work out really well. So we do know that the distance around the track is 100 meters. And the displacement around the track is 0 meters. And that's because we have started and stopped at the same place. So there's nothing there that we can really do. All right, let's go ahead and go to the next one. So the reason that we're going through a lot of this is because they're going to have you explain things. And if you don't know these basic things, you're gonna have some trouble. So even though it's a little bit of review, we really want you to, we really want to make sure that you can see this. All right, so speed and velocity is the next thing that we have to worry about. So I'm gonna just close this guy over. Speed and velocity. So with speed and velocity, same thing. Be really careful because on the AP test, they love to try to make sure you understand what's going on. So speed, remember, is a scalar. It does not depend on direction. Velocity is a vector, and it does depend on direction. But more importantly, velocity depends on the total displacement. Speed depends on the distance. So if you had to find the speed if the trip time is 50 seconds versus the velocity if the trip time is 50 seconds, you're going to know that your average speed here is going to be 2 meters per second, and your average velocity is going to be 0. And the reason why is because there is no displacement when we think about the starting and the ending position. All right. Motion maps. Sometimes there are motion maps on the AP test, and motion maps basically just go through and they show you how a object is moving. So this object is moving at a constant speed in a positive direction. You need to be able to explain why that is. So if I wanted to explain this, I would say that there's an equal space between the dots, and the dots represent a time and a position in that time. So same thing with the negative direction. You'll notice it's going in the opposite direction. All right, cool. So what is acceleration? Remember, acceleration is really just a change in speed. If I increase speed, that means that I have a positive velocity and a positive acceleration, or a negative velocity and a negative acceleration. The other thing that I want you to see here is that if I have decreasing speed, one of these is positive and the other one is negative. So velocity is positive, acceleration is negative. Same thing in the opposite case. I can have a negative velocity and a positive acceleration. So a change in velocity, yes, just like the above. However, you can keep your speed constant and change direction. So if you're turning, your speed will stay the same, but your velocity will be changing because you're changing direction. So just some more motion maps of what's going on. You'll notice that this car or this object or this person is speeding up, and they're speeding up going to the right. The velocity, you'll notice, is increasing because the space between these are increasing. And then down on the bottom, you're going to notice that this is the acceleration, and the acceleration is the same each time. So if they ask you to describe the motion of something using a motion map, this is what they want you to do. The second one, notice the velocity is in one direction and the acceleration is in the opposite direction, which means that this object is actually slowing down. And you can see that by the fact the dots are getting closer together at the same interval of time. So if there's 1 second between each dot, then you'll notice that they are getting closer together, which means that it's slowing down. All righty, so that's speeding up and slowing down. So what's the big takeaway here? If you have a positive velocity and positive acceleration, or negative velocity and negative acceleration, it is speeding up. And they will ask you, is something speeding up or slowing down? You want to be able to answer that. Same thing with positive and negative, or negative and positive. You want to make sure that you can understand that it is slowing down. Okay, so I want you to take just a moment. We're going to practice a little bit. I want you to, in a Google Doc, so what I would do is open up maybe a Google Doc or open up a Word doc, and I want you to take a little bit of time, and I want you to figure out, okay, I would love for you to figure out, I want you to type a response that tells me, and I'm going to pull up a timer here, what's happening with these objects. Okay, so there are there's one object, there are 3 graphs that explain what's happening on that object. And I want you to, in just a brief description, describe the motion of the object. Do that in a Google Doc or in a Microsoft Word doc. Act like you're practicing for this exam, because once you type that response, you're going to copy it, and then you would paste it directly into the testing system that the College Board has. And so I'm going to give you 1 minute to do that. We'll actually put a timer on the screen here so that you can see that timer. And let's make it a little bit smaller here so that we can see what's going on. All right, here we go. And I've started the timer. You have 1 minute to go ahead and do that. All right, go. So one of the things that you can do, if the stream is annoying you, the chat stream, just move your tab over to the right and you won't see them. You have about 10 seconds. 4 seconds, 2, 1, and your time is up. All right, so cool. Let's check and see what this thing is doing, okay? So this object is accelerating in the positive direction. Where do you get that? You can get that right from this part here. It says it is accelerating. In the positive direction, starting with 0 velocity. So there's our 0 velocity, and at position 0. Now let's just say that they just gave you the position versus time and they want you to explain what's happening. Probably the best thing to do is look at this. Put 2 eyeballs here. If you put 1 eyeball there and 1 eyeball here, you will see that this thing is smiling. And because it is smiling, it has a positive acceleration. So you know that much. You don't know, though, most likely what the velocity is unless you go through, and I can see that my velocity is positive here and positive here, but it's more positive. So I know that because it has a positive acceleration and it has a positive velocity, that this object must be speeding up. All right, cool. So that is the first one. Let's go ahead and take a look at the next one. All right, here we go. I'm going to give you 1 minute again. I want you to go ahead and figure out, what can you tell me about the motion of this object? This is going to be something that I almost can guarantee is going to be on the exam because it's so very, very important. I don't know that for sure, but I'm pretty sure. So remember, we said probably the best thing to do, and the chat is off now, so you all can focus. The best thing to do is type your response in a Google Doc copy that and then paste it into the box that's on the actual AP test. That's going to be the best way to do it. Taking pictures can be a problem, mainly because of uploading. Same thing with uploading your docs. That seems to be an issue that they've had the past several tests. It's getting better, but it's not awesome. All right, here we go. So for this one, what's happening? This one, you'll notice that this object is slowing down, or it's accelerating in the negative direction, starting with a positive velocity. So here's our positive velocity. It's starting at position 0. And if you notice, if you only add this graph, if you think about two eyeballs, one here and one there, you would see that this thing is frowning. And because it's frowning, it has a negative acceleration. All right, cool. Excellent job. Let's go ahead and move on to the next one. This is the second to last one, but like I said, I think these are really important. So thank you so much for doing this. I want you to type in a Word document or in a Google Doc what you think that response would be. You're going to do this. We call this briefly explain what this thing is doing. And I'm going to start the timer here. So just to reiterate, I know that I saw in the chat when we had it up, some things that you guys were worried about. Biggest thing is copy and paste your answers. That seems to be the best way to do it. Your answers will be accepted pretty much immediately. If you upload, remember you're competing with about 170,000 other students. And so it will take a while for your response to be uploaded. If you're cutting and pasting, you're more of a direct line right into the College Board servers, and so that'll make it a lot easier. If you want to take pictures and upload, that's okay, but please, please, please practice that on the College Board website on the practice. If you don't know where that is, just type in AP test practice upload, and it'll take you there. All right, your time is up. Let's go ahead and check what is happening with this one. So this object is speeding up. Now, a lot of people say there's no way. Look at this. Velocity is going down. Position's going down, but they're not really. If we look, we notice that the velocity is starting at 0, and so is the position. It's gaining position, but it's going, and instead of saying negative, I always like to say it's going left. And you've seen a car accelerate to the left. If you've ever been to a drag race or just even standing on the sidewalk, cars do accelerate to the left, and we tend to call that negative. That means they're speeding up in the negative direction. And if you look here, we do have a negative acceleration. That means if you put 2 dots above the position versus time graph, you'll notice that that thing is frowning. And when you frown, you're negative. So that's kind of why you see what it is. All right, we're going to skip this last one because we have plenty of other things that we need to do. An object in this one is slowing down. It's accelerating in the positive direction, starts with a negative velocity, and their ending position is 0 meters per second for that velocity. Okay. So here's another way that they like to go through and have you kind of talk about graphing and kinematics. They want to know, when is this cart at rest? When is the cart speeding up? And finally, when is this car slowing down? So maybe just on a little piece of paper somewhere, I would love for you to, or in a Google Doc, that might be even better, so you can practice, type the times when this car is at rest, type when the car is speeding up, and then tell me, when is it slowing down? Go. You want to know, when is the cart at rest? When is it speeding up? And when is it slowing down? All right, just got a few more seconds here. And your time is up. So let's go ahead and check some answers and see what you got. So this car is at rest at 2 times, at 4 seconds and at 18 seconds. Now, a lot of you might have said, oh, no, that's not right. It's at rest from 12 seconds to 17 seconds or from 20 to 25. But notice this is velocity versus time, not position versus time. So be really, really careful with that, okay? The card is speeding up from 4 to 9 seconds, okay? So here to here, it's actually speeding up, and from 18 to 20. It's not speeding up here. Notice you're going from a high negative speed to 0. It's actually slowing down there. So where is it slowing down? From 0 to 4, it's going a high speed to a 0 speed. It is also slowing down from 9 to 11 and from 17 to 18. So that's what you want to do. Now, this is where you get to practice doing the ABCD thing again. I would say that you probably want to do the BCD thing. So do basic physics, cite evidence, and then draw it together. So let's go ahead and let's take a look at this one. It says briefly describe how you would determine the horizontal position of the cart at 7 seconds if the cart is located at 3 meters at time equals 0. You do not need to solve for the final answer. All you're doing here is briefly describing. This is what they're going to do. So please, please, please make sure that you can do something like this, all right? So I'm going to give you 1 minute to type that. Remember, basic physics. Tell me what you can do in terms of basic physics. So think about what is your basic physics for this. Cite evidence, use the graph, tell me what you would do, and then draw it together. All right, here we go. All right, you got about 20 seconds. 10 seconds. All right, your time is up. So for this one, you really need to say something similar to this. Give your basic physics. So I'm going to say the area under the curve on a velocity versus time graph is the change in position for that object. So that tells me how far it has moved. Then I said I would start with 3 meters because remember I started at 3 meters and add the area from 0 to 4 seconds. And I added it because it's above the line, and then subtract the area from 4 to 7 seconds because it is below the line. And then I would just say, since the total area under the curve is the change in position, adding that area to the original position will give me the final position. Remember, it said you don't need to solve for the final answer. If all you do is solve the answer and you just put that answer down and you don't do any of this, you will get 0 points. The whole point of the test is for you to explain what's going on and explain your physics. Please make sure you do that. You will not get points for a correct answer unless you back that up, okay? Super important. All righty, let's go ahead and let's skip this one. It's the same type of thing. This one's a little bit different. It says, briefly describe how you would calculate the acceleration of the object from 2 to 4 seconds. So you'll notice we're doing a position versus time graph. And lots of people say, well, you really can't because it's on a curve, but you can approximate what it is. So the best thing to do is to find the slope of the position versus time graph at 2 seconds and at 4 seconds. So I did that. I found out that it's about 20, and then it's just about 15 or so. Once I've done that, now I can plot those two on a velocity time graph, and I can go through and find out what that average acceleration is. But you have to be careful because they want you to explain. So here's what I did. I said the slope of a position versus time graph is the velocity of the object, and the slope of a velocity time graph is acceleration. I then told them I would do 2 tangent lines, one at 2 seconds, one at 4 seconds, and then find the slope of those 2 lines, find the slope of both of the lines. Plot those values on this chart, and then I can draw it together. Since the slope of the position time is velocity and the slope of the velocity versus time is acceleration, if I find them in sequence and then solve for the slope of this, I can find the acceleration for that time period. So you're doing things you've always done in physics, but now you have to be able to explain them. Please, please, please use something like CER, claim evidence reasoning, BCD, basic physics cite evidence, draw it together, to really do a good job of answering the questions. If you don't do that, you're going to have trouble. All right, I think we're going to skip this one. Same type of thing. You can go through. They want to know which way is it going. I went through and did that, so that makes it a little bit easier. They want to know when is the car at rest. And so this is kind of a trick question, but I was able to go through and use basic physics to explain it, give some evidence, so cite some evidence, and then I drew all that together. Super important for you to do that. All right, and then remember there are 3 kinematics equations on your AP Physics 1 equation sheet and one that is not. Remember this one you use when you don't have and don't need to solve for a change in position. This one you use when you don't need or don't have the final velocity. This one we use when we don't have time. Okay, and then this one we use if we have 2 velocities in a time and we want to find the change of position. So that's basically what you need to know about kinematics. I think the biggest thing in kinematics is knowing how to use the graphs. All right, let's go ahead. We are at 4:52. We still have a little over an hour and a half. That's plenty of time to get through what we need to get through. Here's the next thing I would like to do. Let's talk about forces on a single object. So what do you mean by forces on a single object? So for example, let's say I have this cup and I lift the cup. That is a single object. But on the other hand, let's say that I have a string or a cable, okay? And on one end of that cable, I attach an object. So we're just going to kind of basically attach this here. And then on the other end of this same object, okay, or of the string, I attach another object. So I wrap it around here. And then I put it across the pulley. Now I have a system of objects. So it's important to understand how dynamics works, both on a single object and on a series of objects. So first thing, physical quantity. That's what a force is. It is something tangible. It measures and models both a push and a pull, and it is a vector. So it has a direction, up, down, in, out, right, left, into the page, out of the page. So be very, very, very careful that you always give a direction or you give it a either a plus sign or a minus sign. You give it something similar to that. Magnitude is in Newton. So what are the different types of forces that you're going to see on the AP test? Weight. Weight, simple, very easy to do, but commonly messed up because people will type capital G or just G. That's gravity and that is an acceleration. So if anything, the only thing you really need to get out of this whole page is don't ever put just G or capital G. Those are not weight. One of them is gravitational acceleration. The other one is the universal gravitational constant. Remember, weight is something that depends on gravity. And so it has to be either on the Earth or on some other body that can provide enough gravity to pull that thing really hard towards it. Fg is equal to mg is not on the equation sheet. So please realize that. Instead, it is A is equal to the sum of the forces over the total mass. be very careful with that. We have the normal force. You know that that one's perpendicular to a surface. Tension is parallel to the surface. So is friction. And then we have a spring. And this one is also parallel. So notice the only one that is perpendicular is the normal force. All the others are either parallel or straight towards the center of the earth. They like to try to get you to explain which direction the force acts relative to the object. So please make sure that you understand these. All right, those are the two types of forces. All forces have a couple of things in common. They have an object, and that's a thing the force acts on. So for example, my cup, this is my object. There is a force pushing up on it, okay? And the agent, my hand is the agent pushing it up. Now, there's also a force on this object pulling it straight down, and that's the force due to gravity. It comes from the agent, which is the earth. I am not pulling it down, it's the earth pulling it down. So be very careful when you talk about the object and the agent or the cause and the effect. So we're going to do a little multiple choice here. We have a bird sitting motionless on a porch, and there's two forces that act on this. What I would like for you to do is just kind of think in your head, what are the two forces acting on the bird? And then on a Google Doc or on a something similar to that, maybe on a Word doc, I would like for you to briefly explain how you know. I'm going to give you about a minute or so to do this. And I've talked a little bit, so you've got a little bit more time. But go ahead and pick the two forces. Briefly explain means just use basic physics, sight evidence. You don't have to draw it together or anything else. Basic physics, sight evidence. Go. So don't forget to briefly explain. I think that's the most important part. Remember, they're not looking for correct answers. They're looking for complete solutions. And that includes the answer. Answer is important, but you don't get points for you don't get points for just putting the answer. You have to have your reasoning. About 5 seconds left. All right, awesome. So your time's up. Let's check and see what the answer is. The answer is both A and B, and this is kind of my briefly explain. So the force of gravity I know points to the center of the earth, and the normal force is perpendicular to the surface. So I said exactly what we were talking about on the last slide. I then did the action-reaction pairs. So the bird is pulled down by the earth, and the perch pushes up on the bird. And I said, since the earth pulls down on the bird, that's the force due to gravity. And since the perch pushes perpendicular to the bird off a surface, that is the normal force. So if they ask you to explain, which they're going to do on this test, make sure that you can do that. For the force of gravity, what is the force acting on and by what object does it come from? So I'm going to give you 5 seconds to try to answer this. Here we go. All you have to do is just give me a letter answer. You don't need to explain this one. Go. 2, 3, 4, 5. All right, so it is acting on the bird, and that does come from the earth. Now, if you had to explain it, how would you do that? You need to say something similar to a Newton's third law pair. But if you just write N3L, you're not going to get credit. You need to explain what that means. So here I said it is due to gravity and it involves the earth and the object on which the force acts. I then cited evidence and then I drew it together. If it says briefly explain, you can get away with just doing B and C. If it says write a paragraph length formation, you need to do B, C, D, and make sure that you restate the answers. It's going to be super important for you. All right, here we go. For the normal force, same thing. What is the force acting on and by what object does the force come from? And here we go. I'm going to give you 1 minute again. I do want you to explain. So go. Got about 20 seconds. All right, perfect. So let's check and see what is your answer. So for this one, it is acting on the bird coming from the perch. Again, you can use the Newton's third law pair. It involves an object exerting the force, the perch, and the object on which the force acts. And that would be the bird. So here we can just say, a little evidence, the perch is pushing up on the bird, and as a result, the bird is pushing down on the perch. And then I drew it together. You would not have to do that for a briefly explained, but you should do that for a paragraph length response. Awesome. Okay, so let's go ahead and let's skip this one, and let's take a look at this one. All right, so a skydiver has just jumped out of an airplane and is falling. I want to know what forces are acting on the skydiver. And remember, you also want to briefly explain your answer. All right, on your mark, get set, go. And I know several of you are probably going, hey, I have a question. I have a question about this. Unfortunately, you won't be able to ask any questions on the AP exam of anybody. So you'll have to use your best judgment on this one. All right, time is up. Let's see what answer we did get here. And you'll notice there's actually two forces. Now, why? If they want you to ignore air friction, they will tell you that. Here, they did not tell us to ignore air friction. So that's a pretty common thing that they do. You really want to explain and talk about both the force due to gravity and the force of friction. So that's why I put this one on here. Notice it does not say the forces of friction are negligible, or it does not say ignore friction. So you have to include it. Plus, what would the fun of skydiving be if there was no air? That'd be tough. All right. We're going to go ahead and skip this because we kind of know these. So we'll move on there. All righty. Let's skip this one too, because I think that one is just a little bit different. All right. Newton came up with how many laws to describe motion? Okay, so think about it. In fact, what I would do is you can just put up 1 finger, 2 fingers, 3 fingers, and you are correct. There are 3 laws. So remember, there is the first law, the second law, and the third law. But be really careful when you're explaining these. And here's why. Very commonly, when you say Newton's first law, you say an object in motion stays in motion and an object at rest stays at rest unless acted on by an outside force. That's really bad. Don't say that, okay? Because if you look, this young lady here, she is at rest and she stays at rest. But there is there are several different outside forces acting on her. The earth is pulling her down. At the same time, these people are pushing her up. This young lady is pulling her that way, and this young lady is pulling her that way. Okay. There are several forces acting on her, and they're outside of her system. It's a terrible definition. So please never say an object in motion stays in motion and an object at rest stays at rest unless acted on by an outside force. That's not true. Here's what you need to say. If there's no net force acting on an object, so she is stationary because there's no net force. There's no force pulling down bigger than the force pushing up. There are two forces there. There's also a force to the left of her and to the right of her, and she is pulling equal and opposite on those. So there's lots of outside forces, but don't say there's no outside forces. Make sure you just say there's no net force. When these people let go of her, there is now a net force down, and she will fall, but then they will catch her. And you could talk about the net force pushing up to make her accelerate upward so she slows down. So anyway, just be really careful with that. Next one, poor definition of Newton's second law. Force equals mass times acceleration. Okay, that's awesome. But let's look at this. This person is holding these still. There's a force, there's a mass. Oh, there's no acceleration. So again, let's change this. An object's acceleration is a result of the net force on the object divided by the object's mass. Since the net force here is 0, that makes the net force 0, or the sum of the forces 0, so these mean exactly the same thing, then that means that your acceleration has got to be 0. But if you look down here, there is a net force on the little tiny tree that this guy pulls out of the ground. And because there's a net force on that mass, there is an acceleration. So that's our definition. An object's acceleration result of the net force of an object divided by the object's mass. That's why it's on the equation sheet that way also. All right, let's think about Newton's third law. Newton's third law, for every action, there is an equal but opposite reaction. But you know what? If you pull a child in a wagon, the wagon moves forward, so that can't be equal and opposite. He can't pull on the wagon to accelerate his little sister, and then she can't all of a sudden then try to travel in a straight line while he accelerates it towards the center, right? So let's change that definition. If A exerts a force on B, so if the boy exerts a force on the handle, that handle exerts a force back on the boy. And then the handle exerts a force on the wagon back on the handle, then the wagon on the girl, and the girl back on the wagon. But why does the whole thing move forward? Because the force between the kid's feet and the ground is bigger than the force between the wheels and the ground. So remember, friction here is pushing the child forward, which means the child's pushing back. But that force is much bigger than the little tiny force, the little static friction force that is keeping the wheel from sliding. And so there's a bigger force coming from this person's legs than coming from the wheel and the surface. But between the arm and this, between the wagon handle and the wagon, and between the girl and the wagon, those are all equal and opposite. So be very, very careful. All right. Apollo 13 is a 1995 movie. You kind of know about it. In the movie, one of the astronauts says, well, we just put Sir Isaac Newton in the driver's seat. So he was talking about Newton's first law. When does he mention this? So think about Newton's first law. I'm going to give you 10 seconds to pick an answer. You don't have to explain anything. And go. Got about 7 seconds left. All right. So Newton's first law means that there is something moving, okay, or not moving, and the sum of the forces is going to be equal to 0. So for this one, the spacecraft has finished firing its engines and has spent all of its fuel, and it's just coasting through space. So there's no acceleration there. All right, let's look at the next one. You have an aircraft flying to the right, constant horizontal speed of 200 meters per second, and there are these 4 forces. If that condition continues, which direction is it going to fly? And you have 5 seconds to think about this one. All right, awesome. You should have picked letter D, but they don't really care that you picked D. They want to know why. So at this point, you would say, according to Newton's third law, the sum of the forces is going to be equal to 0 in the x direction and 0 in the y direction. Since the plane is moving from left to right, this means it will continue to move left to right. And since the plane has no net force in the vertical direction, it will not accelerate up or down. Therefore, it will not do A, B, C, or E. It will only continue at D. That's the key. I know this looks really easy, but it's difficult to explain, especially if you aren't using the physics and using the physics correctly. So please make sure that you're using the physics correctly when you do it. All righty, so next one. A skydiver falling through the air opens her parachute. The skydiver and the parachute together have a weight of mg. At a specific instant after the parachute opens, a force of air resistance on the parachute is 1.4 mg. They want to know what is acceleration. So this is kind of one of those thinking questions that you can do without having to really show any math. They would say, how would you solve this? They would not ask you to solve it. They would ask you, how would you solve this? So if you did this correctly, you would find out that it should be accelerating upwards because the force of air resistance is opposite according to Newton's third law, and it follows Newton's second law because it has an acceleration due to a larger net force or a sum of the forces pointing up. All right, cool. This one. They want to know which of the following diagrams. So every year, probably one of the best loved questions is the ones where you get to draw a free body diagram, because typically they're pretty easy and you get, some pretty easy points. This year, you won't be drawing anything. Instead, they're going to give you a scenario like this. They're going to say which of the following diagrams best represents the forces acting on the car, and briefly explain your reasoning. So please make sure you understand that you need to explain your reasoning. If you're looking for some more things to practice, pull up an old AP Physics 1 exam, but don't use the free response. Use the multiple choice. And when you use that multiple choice, what you want to do is try to explain why that answer is correct. All right, so I'm going to give you just about, let's give you a minute to go through and do this, but I also want you to type up a response that explains why your choice is correct. So you're either going to need to talk about 3 or 4 forces, kind of depends. All right, here we go. For those of you that have kind of popped in a little bit later, we have been talking about the AP exam and how to best answer the questions. We said to do 2 things. One of them is have some writing way that you do it. So like basic physics, cite evidence and draw it together, plus answer the question, or claim evidence reasoning. But more importantly, you have 3 choices. I would choose the first choice. That first choice is to copy and paste your answer into the actual test itself instead of uploading a picture or uploading a document. We found out that the people who are having the least problems are just typing it on a Google Doc and then copying that and pasting it straight in. That seems to work really well. So you got about 1 second and time is up. Beautiful. All right. So the answer to this one is actually letter A. We know that there really is not a prescribed force. So lots of people like to pick this one. What is the force going forwards? There isn't. The force going forwards is friction. It's because the car is pushing backwards on the hill. And so there is a force of friction actually then as a reaction pointing up the hill. The normal force, notice it is perpendicular, and then the weight force points straight down towards the center of the earth. To briefly explain, you would need to do what I just did. Normal forces, basic physics, are always perpendicular to the surface. Weight force is always pointing towards the center of the earth or the center of the massive object. And then the friction force, when something is climbing a hill, is in the direction of motion. It does not oppose the direction of motion. We're trying to go up the hill. So that's really important. And those are the three forces on that one. All right, so I think what we're going to do is that is really the end of single forces. We need to spend a little bit more time thinking about a system of objects and the forces on that. The last thing that I'm going to do is talk about energy, and we're going to probably spend the most time on energy. We'll probably spend about 50 minutes on energy. So we're going to spend about 20 or 25 minutes on forces on a system of objects. So this is a good system of objects. You'll notice that the force is not acting just on one object. There's several forces acting on all three objects. They want us to find the action-reaction pairs. So for this one, if we start on the left, we'll notice that there's an action-reaction pair between the tire and the road, then between the tractor and the rope, between the rope and the hand, between the rope and the hand, between the rope and the elephant, and then finally between the elephant's feet and the ground. And if this thing is in static equilibrium, that means each one of the action-reaction pairs is equal and opposite. So whatever the wheel and the road here has, if there is a 5 Newton force in one direction, there's 5 in the other. That has to be equal to the 5 Newton force between the elephant's feet and the ground, or the whole thing would shift. And then there might be a smaller force in some other places, but that's kind of what you want to do when you start looking at a picture. Don't just look at this person in the middle. Also look at what's going on everywhere, including the ground. They are going to also have you think about systems. If we just think about the ropes and the person, that's a different system than the rope and the person on the left. The rope, the person, and the tractor on the left, or the rope, the person, and the elephant on the right. Be very careful with when they ask you a question that your system, if they define it, you only use that system, and recognize everything outside the system is an external force. Remember Newton's second law. This is on your AP Physics 1 equation sheet. Super important that you've printed off your equation sheet. I would print it off and then scratch out the equations for electricity and electrostatics. There's no electricity and electrostatics on that test, so please scratch that off. This equation is super important. It defines a lot what we do for forces. Remember Newton's third law, the best definition is if A exerts a force on B, then B exerts a force on A that is equal in strength and opposite in direction. But for a system, we said that we could look at all the forces and then think about how all the forces interact. So we have two cases of where those forces interact. There's no movement at all, or there's constant velocity. And if we don't have any acceleration there, we would say that the sum of our forces is equal to 0. So if something is not moving or has a constant velocity, then there's no acceleration in both of those cases. That also means that the net force, or the sum of your forces, should be 0. For the next one, if I have unbalanced forces, then the thing has to be doing one of two things. It either needs to be speeding up or slowing down. And earlier, remember, and I saw some of you were commenting, this is so basic. Why are we doing this? Because it directly relates to how you define speeding up and slowing down, which then directly relates to unbalanced forces, which then directly relates to things like Atwood's machines or inclined planes and how they work. So without the basics, you're going to have a lot of trouble explaining kind of what's going on. All righty. So let's see what you know. While driving down the road, a grasshopper strikes the windshield. So you'll see this here of a bus and makes it quite obvious that the mess in front of the face of the driver. Which of the two forces is greater, the force on the grasshopper or the force on the bus? So I will give you about 10 seconds to think about that. All right, time's up. Your answer is, oops, sorry. Your answer here, it is the same for both. Now, a lot of people say, yeah, but look at the bug. It's not a bug anymore. You're right, it's not. But the force on the bug is the same as the force the bug gives on the bus. The question is, which one had a greater acceleration? Well, obviously the grasshopper. The bus, if it's going 65 miles an hour, is still going 65 miles an hour going down the road. But we could say 64.99999999999. That means that the grasshopper, if it was flying at 5 miles an hour towards the bus, after it's the bus, it's now going 64.9999999 miles an hour. It had a huge change. So now we need to think about impulse and how that would affect what's happening with the grasshopper. Before you do a problem, you need to kind of think about some things. Think about how would you draw the free body diagram, remembering you're not going to draw it. Instead, you're going to go through and you're going to have to go through and describe what that diagram looks like. Or more than likely, they're going to do what I did and give you a diagram, and you're going to have to tell whether that free body diagram, first of all, is complete, and second of all, if there's anything wrong with it, and then explain how you know. The last thing that you probably need to do is be able to find the sum of the forces, but not quantitatively, not with numbers, but qualitatively. What would make up the sum of those forces? So here we did say that this is the same for both. And it's because we know that the acceleration of the grasshopper is huge, but the force between the two things is exactly the same. All right, many people are familiar with the fact that a rifle does recoil when it's fired, and that recoil is a result basically of just any action-reaction force pair. So a gunpowder explosion, it creates a lot of hot gas that expand outward that allows the rifle to push on the bullet. If we think about Newton's third law, we know that the bullet then pushes with an equal and opposite force back on the rifle. But the big deal here is one of them has a very large mass and the other one has a very small mass. So think about it that way, okay? Same thing with the bug and the bus. One had a big, one had a small mass. And if the force is the same, think about what the proportional reasoning would be between the bullet and the gun itself. So for this one, we know that the acceleration of that recoiling rifle should be much smaller. And you have to use A is equal to F over M, where we know F is the same, but because the mass of the bullet is so small, the acceleration has to be huge. You should be able to explain that as you go through. If you can't explain it, you won't do as well on this exam. Getting the answer is one thing, but being able to explain it, remember, is the most important thing for this exam. All right, I really like this one. So this is number 3. In the top picture, we have Kent move it, and Kent is moving, pulling on a rope that is attached to a wall. In the bottom picture, Kent is pulling on an elephant, and there is a force scale for each one, and they both read 500 newtons. So the question is, Kent is pulling either A, with more force than when the rope is attached to the wall, with more force when the rope is attached to the elephant, or it's the same in each case. I'll give you 5 seconds to think about that. So from this picture, you can see that nothing's moving. And if nothing's moving, the question is it accelerating? Well, sure, they could both be accelerating, right? But there's no net acceleration because there is a force of 500 newtons in the string between the two, but neither are going anywhere. So it is the same force in each case because it's stationary, and we see what the force is right here. That force is the same. All right, so this is a really good question, and it just kind of shows you how you need to think about drawing free body diagrams. So on this one, I want you to think about how many arrows I need to draw and in which direction. So then we're going to show you the picture, and then we're going to talk about how they're going to put this on an AP exam. All right, so I'm going to give you about 30 seconds here to think about that. And if you want to, one thing I would highly suggest you do is always have a piece of paper out for your exam, so that if you do need to draw something and then explain it, you're able to do that without having to do it in your mind. Makes it a lot easier if you draw it. Typically, when you draw it, now you're active and you're really thinking about it. The other thing you could do is have a whiteboard. Whiteboards would also be awesome to use for this. Okay, so if you had to describe the drawing, one of the forces that you would have to describe is the force due to gravity that would start at the dot and then would point straight down. It should be labeled mg. You then should have the normal force starting at the dot and would point up and to the right, but the key word here is perpendicular to the surface. If you just say up and to the right, you will not get credit. And it's because you have to say up and to the right, perpendicular to the surface. Remember the words parallel, perpendicular, and then finally straight down towards the center of the earth are the three important things to explain when you talk about drawing a free body diagram, since you can't draw it. The force of push would be parallel to the surface and point up and to the left, starting at the dot. Always start at the dot. And then the force of friction would be pointing down the hill, down to the right, starting at the surface, and would be parallel. Now notice this object's moving up, but the force of friction is down to the right. It's because now we have a pushing force that's making it slide up. And so there's a force of, is it static or kinetic friction? Think about it. Correct. It is kinetic friction because they're sliding. Okay. Sliding, kinetic. Static, they just touch. There's no sliding. So that's how you would explain that one. Remember, we did talk about the paragraph length response. We said that you always want to answer the question first, do basic physics, basic principles, or basic equations, cite evidence, and draw it together. And we also, remember, said you probably would be better off doing BCD/A, where you're doing basic physics, citing evidence, drawing it together, answering the question, or you could even do CBDA. But you got to try to involve all of those on a paragraph length. So here is a really good question. It says the graph below shows the net force in the x direction acting on a cart as a function of time. They want us to rank the acceleration of the cart at the labeled times. Ooh, graphs again, yes. So realize that in every single unit, they might be, they probably will have you at some point in one of the units describe what's going on based on a graph. So remember, there's two things for every graph you need to know. You need to know what the slope represents, and you need to know what the area under the curve represents. So please be very, very, very careful that you understand that you could use either slope, or you could use the, I'm setting a timer here, slope, or you could use area under the curve. So I'm going to give you about a minute. I want you to rank the acceleration of the cart at the labeled times. So A, B, C, D, E, and F. If any of them are equal, just put an equal sign between them. But always notice that this is the greatest, okay? So this one's going to be greater than the next one or equal to it. You could also say that the cart, the acceleration is the same but not zero, the acceleration is zero, or the ranking acceleration cannot be determined. So I would type your answer into Google Docs or in a Word doc. If you're going to handwrite your answers, we would prefer you don't. It's sometimes hard to read what you write. It's often that when you're doing this, you use a pencil and it's too light, especially when you take a picture when you take a picture, there can be glare, can make it really hard to see your pencil. If you're going to do this, use pen, but 100%, there's really no reason to take a picture and upload. There's really not a lot of reason to type and upload a PDF or a doc. Best way to do this is to type, copy, and paste. And that's probably the easiest thing to do too. So I'm going to give you just a little bit more time here. All right, cool. So now your time is up. Let's kind of check what the answer is here. So C is going to be the biggest acceleration. Then B, which is going to be equal to D. And then F, and then that's bigger than A, which is equal to E. So how did I know that? What I did was I just said the net force on the system is equal to the acceleration of the system times the mass. So that's just Newton's second law. If you just say N2L, it's not enough. You need to show the equation or explain the equation, one of the two. The points represent the force and the acceleration of the cart, and they are proportional to the net force. Since the mass is the same for this thing, we know that F equals ma. If you get rid of the m, F is proportional to A. And so the bigger the force, the bigger the acceleration. So now I can say that since the acceleration of the cart is proportional to net force, the ranking follows the force values. And that's why my answer is the way it is. If you just rank them and you don't put anything else, even if your ranking is right, you will get 0 credit. I can tell you that. I've graded these for the past 5 years. This will be the 6th. And we don't give points for just an answer. We really are giving points for an answer with a really good explanation. If you just have the answer, you just don't get any credit, correct or incorrect. All right, here we go. Next one. So shown below are boxes. These boxes are being pulled by ropes along frictionless surfaces. So remember, if it's frictionless, they will tell you. Otherwise, you can assume that there's friction there. Accelerating towards the left. All the boxes are identical, and the accelerations of the boxes are indicated in each figure. They want you to tell what is the tension in each of the ropes. If when you do this, make sure that you're ranking them from biggest to smallest. Do it by letter, A, B, C, D, E, F, so you can put the letters wherever you want to. Do largest to smallest. If you think they all are the same, you can just say that. Or if you don't think you can find it, but you still have to explain why you can't find that. Do the same thing again. I would give the answer, then at least do basic physics and side evidence. Try to draw it together if you have time, and you should be good. All right, here we go. I'm going to give you another minute to do this. Go. Have about 10 seconds left. All right, you got just a couple seconds. And good job. All right, here we go. Let's check our rationale and our answer. Your answer, not that it's huge, but it helps you get more points, is B is bigger than D, which is equal to A, which is greater than C, which is equal to E, which is greater than F. So what's our basic physics? Basic physics, again, is the same thing. The net force on a system is equal to the acceleration of that system times the mass of the system. And since we know the tension, which is a force, is equal to the mass of all the blocks to the right of the rope times the acceleration, The ranking for each is just the total mass of the system behind the rope times acceleration. So here's what we're going to do. We know that the tension in rope B is 2 masses times 2 acceleration, and that gives me 4. If I look at letter D, notice I have 1, 2, 3 masses times 1 acceleration. So that would give me a value of 3 for tension. For letter A, 3 times 1 is 3. So those two are the same. The tension in this rope is the same as this one. For letter C, I have 2 accelerations times 1 mass. So its tension is just 2. Letter E is also 2. Now, why is letter E 2? Well, I have 1 acceleration for the entire system, and then I have 1, 2 masses. So 2 times 1 would be 2. So both C and E, so C, not the block, but the string, and the string E have exactly the same tension. And then finally, letter F, it's 1 acceleration, 1 mass. So it is just 1. All right, cool. That's a really good one. I really can see them doing something similar to this in a part of a problem. Remember, all these things that we're doing are actually parts of problems. More than likely, there's going to be part A, B, C, D, E, F, and you're going to try to get as much of that done as you can in your 25 minutes for a qualitative quantitative translation. In a paragraph formation, there'll probably be fewer parts, but in a qualitative quantitative translation, you're going to find yourself answering the same question in a different way over and over and over again, and that's okay. But you've got to do it well. Make sure you include your basic physics. All right. I keep trying to remind you guys of that, so hopefully that helps. If we look at this question, this is another good one that could be like a paragraph length response. Box A is on a table and it has box B on top. A horizontal rope is pulling box A to the right with a force F. There is friction between the boxes. So here they told us there's friction. They want to make sure we know that. Between the box, the lower box and the surface, and between box B and box A. The top of box B is at rest relative to box A, and both boxes are accelerating to the right. A student draws, not to scale, some free body diagrams. Oh, look at this. So what they've done is they have drawn these, and what I'm going to do is get rid of that little box right there, make it a little bit easier to see. There we go. And they want you to figure out there's at least one thing wrong with the free body diagrams. They want us to go through and identify all the errors and explain how to correct those errors. So I can see them doing something like this. Since you can't draw free body diagrams on the exam, they don't want you to do that. They don't want to have you try to figure out how to do that. And they didn't want everybody trying to upload huge files of pictures. That's the other reason why it's probably not a good idea to do that. They want you to explain what's wrong. There's at least one thing wrong with the free body diagrams. So identify all the errors and explain how to correct that. And what we'll do is we will give you a good 2 minutes to try to figure that out. Okay, so go.
Hey, Christian. Hey everybody, if you're experiencing any errors with the stream, I just want you to try a couple of things. I want you to log out, clear out your browser cache for crowdcast.io, and then try logging in incognito mode. Make sure you have all ad blockers disabled. Any pop-up blockers that you might have installed, and make sure those are disabled to
you have
sure
about 1 minute left to try to figure out what might be wrong with the free body diagrams there on the bottom. Remember, this is just a picture. It's not a free body diagram. This one is the free body diagram. So you got about 25 seconds. About 5 seconds now. All right, cool, good. Now, hey, let's check and see what answer you got. So if we look at box B actually has some, looks like maybe all the forces. A looks like it has all the forces, but there isn't. There is a force missing on box A. So in the system, we know that Newton's third law states there should be an action-reaction pair to each force. There is a force missing on A. It's the Newton's third law force pair to the static frictional force E on box B. So there's a force on box B going this direction, and it is keeping that box on letter A. But we don't have an equal and opposite force coming off of A going in this direction. So we really need to add another force going to the left. All the other forces are here. So therefore, on A, there should be one more vector directed to the left representing a static frictional force on A from B. Otherwise, that box on top would actually shoot off to the right because of that extra, shoot off to the right because of that extra force. Okay, let's go ahead and take a look at this one. So shown is a spaceship pulling 4 cargo pods at a constant velocity. They're connected to each other by rods, and the rod connects pod A to the spaceship. So notice these aren't strings, they are solid rods. The velocity of the spaceship and of the pods is 5,000 meters per second. All the masses are given in terms of m, the mass of the empty rod. And you don't have to worry about any resistive forces. So remember, we said they would tell you if you have to figure out, ooh, there's friction, or there's no friction at all. All right, cool. So rank the magnitude of the tension at the labeled points in the rods. So there's A, B, C, and D. And then you'll rank them from biggest to smallest. Or you can pick they're all the same but not 0. You could say they're all 0, or you could say you can't determine those, but then make sure you explain your reasoning. So same thing again, I'm going to find my timer that I just lost, and we will give you 2 minutes to answer this one. All right, here we go. Remember, you want to be doing this either on a Word doc, in a Pages page. I'm not sure anybody uses Pages anymore on the Mac, but you might. You can do this on OpenOffice and Microsoft Word. And then when you get done, you would want to take that response and post it. Oh, BCD means basic physics. C is cite evidence. And D is draw it together. Hey, you are awesome. Thank you for doing that. I appreciate it. Yeah, basic physics, cite evidence, draw it together. Yeah, they do look easy, and they're not. You got it. So right now we're talking about forces on a system of objects. All right, here we go. Okay, time is up. Let's find out what the answer is. I think I saw some of you have the right answer, and your answer is the tensions are all 0. Why are they 0? So remember, the net force, which is what we're looking for, is tension. And because if you look, it says they're traveling at 5,000 meters per second. It does it 2 places, here and here. There's no acceleration. So the net force on a system is equal to the acceleration of the system times the mass. And for the net force to be 0, the tension has to be 0 because that is your net force, is your tension. And since the velocity of each pod is constant, there's no acceleration at all. And therefore, there's no net force. So remember, A is answer the question, B is basic physics, C is side evidence, and D is draw it together. So great, great, great little example of a really nice paragraph length response that would take you about that 15-minute time. So you guys are doing excellent. All righty, so I think, yeah, let's do this one. I really like this one too. We have various stacks of blocks traveling along a conveyor belt, and at the instant shown, all the blocks have the same velocity of 3 meters per second to the right, and the same acceleration of 2 meters per second squared also to the right. The blocks don't slip. Now, here's the key. Be very careful. It can't have a constant velocity and an acceleration. But notice they didn't say it had a constant velocity. It says at the instant shown, the velocity of all of them is 3. But they are accelerating at 2. They want to know what is the net force on each stack of blocks. So make sure you go greatest. Yeah, these are from tippers to the least. But I'm having you explain these using that B, C, D. So that is the way to do it. And let's give you 2 minutes again. Here we go. Yeah, I think we just put this here. So we're ranking the magnitude of the net force on each stack of blocks. Yeah, I'm not going to stop. I'm going to keep going. There will be a break at 6:30 so that you guys can not miss anything at all. And so that'll be then. But if you really need to go somewhere, go and come back. But we will just keep going until 6:30, and then we'll have just a little bit. You will not have to derive equations. You will not have to derive equations. Yeah, 6:30 Eastern time. So sorry. You're absolutely correct. 5:30 Central. So we have about 30 seconds left. Break will be about 5 to 10 minutes. Yeah, you might have in physics too. And we have about 15 seconds left for this one. And we'll take a look at the answer. You do not need to derive on this test. All right, here we go. And so here is your answer. A is equal to D, then B, and then C is equal to E. Remember, the net force on the system is equal to the acceleration times the mass. And if you notice, the mass is not the same for all of these, but the acceleration is. So the acceleration is proportional to the mass. And so when we go through, since the force is proportional to the mass, that's really what this should say down here. Stack A has 9 masses, and so does D. So those are the same. That's bigger than B, which is bigger than C, and that is equal to E. All right, cool. Good job on those. Now we're going to do one more unit before we take a break. And this unit is probably the most important of all, and it is energy. Energy is the thing that kind of links everything together. If you don't understand how energy is conserved, or when it's not conserved, where it's coming from, and that's called work, then you're going to have a little trouble on the exam. So please make sure, if you're really having trouble with energy, you can go to Fiveable, and they have some great study guides. You can go to Khan Academy. You can go to Flipping Physics is awesome. So a lot of things like that really are super helpful. There are many different types of energy. Make sure you understand the different types of energy. There are 3 types of energy here right at the beginning. There is kinetic energy, gravitational potential, and spring potential energy, okay? Those are the 3 that you really need to worry about, and we term those 3 mechanical energy. So any and all of those 3 compose mechanical energy. We also have some other energy. So we can think about these as dissipative energy. So this would be sound energy, light energy, electrical energy, and chemical energy. And then we have internal energy. Sometimes we call that thermal energy, and that's what gives you, temperature. So kinetic and potential, remember, that's mechanical. And then sound, thermal, and light, those are all dissipated forms of energy because those spread out in all directions. If I clap my hands just like that, then the energy that's dissipated from kinetic to potential, so there's no potential here, it's just stopped, is sound, okay? So I have just conserved total energy, but not mechanical energy, all right? So be really careful with that. Work. So make sure you understand work. Work is just change in energy. That's all it is. But work is a scalar. In fact, all energy is a scalar. If you have kinetic energy, okay, that's a scalar. Potential energy is a scalar. So be very, very, very careful. If you have a force and that force isn't constant, you can represent work by force distance graph. Okay, work is the area underneath of that graph. We know that force has the ability to transfer energy from one thing to the other. And we can talk about work being positive and work being negative. So if you lift something, okay, my force is up and my displacement is up. So that's positive work. If you let something down, so if I take a plate and I am lowering it down to a table for somebody that I'm serving, I'm actually doing negative work because I'm pushing up, but the plate is moving down. If you do something and the force and the direction are perpendicular, then you're not doing any work at all. Okay, so if you carry something across the room at the same height, you're not really doing any work. Last things, work energy theorem. That is where you have, basically you're just saying that you start with maybe kinetic energy, you end up with less kinetic energy, but you have work. So that'd be like a plane flying through the air or a glider. So it would slow down, but it would then give off heat energy. System can have kinetic and potential energy, and so you can also think about the work energy theorem as what we have below. All right, here we go. Conservation of energy. Please make sure you understand this. If you have conservative forces, So what's a conservative force? That is a force that changes kinetic energy into potential, or potential into kinetic, and there's no loss. So if you think about a spring or gravity, those are conservative. A non-conservative force is one that takes kinetic energy and changes it into things like thermal energy or sound. So that would be friction or air resistance. Those are the two types of forces, so watch out for those. Conservation of energy can be used to analyze a situation if that problem relates position and speed. So make sure that you see that. This is a really good little demonstration of mechanical energy and how we can look at a system. So for example, if I'm looking at just the block, notice the block is moving across the table and down to the floor. So the mechanical energy, when I just think about the block, is only kinetic. Sorry. If you look at the system and it includes the system between A and between A and B, the mechanical energy increases because it is speeding up. From B to C, it remains constant because it travels at a constant speed. And then from C to D, that kinetic energy of the block only gets bigger. If now I think about the block and the earth, I can include gravitational potential energy. If I look at the block and the spring, I can look at kinetic and spring, but not gravitational. And then if I include everything, notice that mechanical energy is kinetic plus gravitational plus spring energy. That's the ultimate. And you'll notice that when you have all of the parts of the system, your energy remains constant the entire time. Otherwise, it will increase as your object moves. Notice you don't see any decreasing mechanical energy, right? So that's super important for this. All right, here we go. We're going to do a little ranking again. And this first one says, shown below are the graphs of velocity versus time for 6 objects that move along a straight horizontal frictionless path. A single external force acts on each one. The mass of each object is given. Now, we did this at the very beginning, and I know some of you are saying, this is super easy. Why are we doing this? Because now you're going to use it. So now we have a velocity versus time graph. You have a slope and an area for that graph. You'll have to figure out which one to use. And they want you to rank A, B, C, D, E, F in terms of the work done. So which one has the greatest work, which one has the least, and if they are equal, just put an equal sign between them. If you can do that when you're done, and you have an answer for just the ranking, you can put that in the chat. If you, when you do your reasoning, just kind of do that in a Google Doc. So just do that in a Google Doc. I'm going to give you about 1 more minute to get your ranking and explain your reasoning. Starting to see a ranking there. Remember, energy is probably the topic that they're going to really, really focus on. But within energy, you can do almost anything. In fact, you can't do anything. So you can do force, you can do kinematics, you can do simple harmonic motion. So there's lots of things like that we can do. All right, your time has expired. Let's check and see what the answer is for this one. So for this one, E and F are the same amount of work. Those are both bigger than C, which is bigger than A, which is equal to D, which is greater than B. So from the work kinetic energy theorem, so this is our basic physics, the work done on the object is equal to the change in kinetic energy. So if we rank that kinetic energy change of the objects, the ranking of work done by the external agents is going to be the same. So really here, the change in kinetic energy will be proportional to the change in the square of the velocity times the mass. So for this one, for letter E, you'll notice that we have 1/2 of the mass, which is 8 kilograms, times our velocity here, change, which is 4 minus 1. And so you get 12. That's equal to F, which is equal to 12. That is greater than C, which is equal to 6. Both A and D are 0. And finally, that's greater than letter B, which is -6. All right, cool. So let's go ahead and move on to the next one. So for this one, we have a 10 kilogram box. At rest, it's pushed a distance of 8 meters. And that is pushed along a smooth horizontal floor. A graph of the applied force of the block on the block as a function of displacement is shown below. So we know the force on the block and we know the position. You don't have to worry about time on this one. So they want to know, will the work done by the applied force over the first 3 meters be greater than, less than, or equal to the work done by the applied force during the subsequent 3 meters? And this would be an excellent paragraph formation. So please make sure you, on a Google Doc or in Microsoft Word or in Pages or in a text editor, go ahead and type your response. That would be the way to do it. And we will give you 2 minutes again to try to get this one done. Remember, you want to work as quickly as you can on the exam, but you still want to be thorough. There will be several parts. Don't worry if you don't get done, that it is designed that way. So on a 25-minute question, that question was really written to be answered within a 50-minute time period. So for you to do that, you'll have to just kind of go through and take your time, do the best you can. It's better to be complete and thorough than it is to rush through it. So be really, really careful with that. And remember, once you pick the greater than, less than, or equal to, you'll want to use B, C, D to try to figure it out. We have about 28 minutes, and we will take a quick 5-minute break. And then Peter Apps is going to come in and run the next 2.5 hours. You guys are awesome. Absolutely awesome for being here and doing this with us. This is our favorite thing to do, is to help you guys try to do the best that we can. Oh, A, B, C, D. So A is answer the question. B is basic physics. C is cite evidence. And D is draw it together. If you can do those, you can do that. You have about 15 seconds. Thank you for typing that. I appreciate it. Yeah, and you know, I think on these last few, what we'll do is when you answer, I'm going to have you answer in a Google Doc or whatever, and then we'll have you paste your responses in the chat. That'll take up some of that flutter that some of you guys are doing in the chat. All right, so for this one, let's see what your answer is. The answer here should be less than. And because in the first 3 meters, we know that the area under the curve is going to be force times position. And remember, work is applied force times position. And so how do I find the area of this? Well, I can't just multiply 3 times 2. That'd give me 6. That would be too much. But if I take 3 times 2 and then divide it by 2, remember for a triangle, it's 1/2 base times height. And that is 100% on your equation sheet. So don't forget the area of different objects or different geometric shapes is on the AP Physics equation sheet. So here the the area of the triangular region between 0 and 3 is less than the rectangular region of 3 to 6. So if you go from 3 to 6, that would be 3 times 2 is going to be 6 for the box that you see here. And that is the best way to answer that one. All right, here we go. Next one, let's give you 2 minutes. This time, I would love for you to go ahead, type your answer into into a Google Doc and or into a Word doc. And then what we'll do is we're going to turn the chat off for the 2 minutes. And then we will turn that chat back on when you guys are at the end of the 2 minutes, and we will have you paste your responses into the chat. So hopefully this gets you kind of ready for the AP exam. So thank you for turning off that chat. That's awesome. And we'll have you read the question and answer it in a Google Doc or in a Microsoft Word document, Pages doc, text doc. Don't forget to do B, C, D, A or A, B, C, D. Answer the question. Basic physics. Cite evidence. So use the graph to give us evidence. And then draw it together. If you want to do B, C, D, you can do that. Got about 50 seconds. They're not going to worry too much about spelling here unless it's really terrible and they can't figure out what it is. So if you make spelling errors, that's okay. From what I've been told, they won't have you type in Greek symbols. Instead, for an angle, they might say, let's call the angle capital D. And you would just type in capital D for the angle. All right, you have about 10 seconds. So this one is very similar to the last one in that we're trying to find out how much work is done. But this time you do have a triangle, you do have a rectangle, you have another triangle, but notice from 8 to 10, you don't really have a shape. So you've got to be able to explain these. So here we go. B, so letter B, which is 2 to 4, is bigger than C, which is 4 to 6. Now, notice that this does not make a shape that you typically can recognize, okay? So you might need to break it into the rectangle here, the square here, and then the triangle here. If you could do the formula for this, would be kind of hard to do. You're going to have to estimate about what this point is. So just kind of be careful there. And we know that this ranking is true because the work done, here's our basic physics, by the applied force is equal to the area under the force versus position graph. So here I did the math. I tried really hard to kind of be consistent with what I was doing, and those are your answers. So hopefully you answered correctly on those. All right, good. Here's one that's got some springs in it. I know on the AP Physics C exam, they did have some springs. They like spring energy. It seems like they have a spring energy question on it every single year. So the figures, oh, you know what? Let's do this. Let's pop that chat back on. And why don't y'all, we'll give you about 10 seconds to paste your answer in. If you did it, good. Good job, Zach. Excellent, David. Good job, Emma. Good job, Aparna. Ashley, good. Lindsay, Stella, good. Neck, good. Brianna, good. Yeah, you guys are doing what we want. That is awesome. Look at that. All right, you guys have the right idea. This is cool to see. Absolutely love this. You guys are doing beautiful. Yeah, and then there's Ryan. Come on, Ryan. All right, good job. Excellent job. Excellent, excellent, excellent. All right, let's go ahead and pause the chat again, and we will do another one. That was beautiful. You guys are doing beautiful. That's awesome. Thank you for putting those in that way. That will help you on the exam. All right, here we go. The figures below show the systems consisting of, oh, we'll pause that chat again. Each block is resting on a frictionless surface in each case. Student pulls on the block and stretches the spring to the right by the distance given in the figure. The mass of the block and the force constant of the spring are also given for each case. Remember, spring constant tells you how strong the spring is. So make sure you take a look at that as you go through. They want you to rank the systems on the basis of the work done on the block spring system by the student. So be careful with this one. And we will give you 2 minutes again to answer. So we'll put the little timer over here. I know it's off to the side, but you can see the time. And go. We'll do the same thing. We'll have you copy and paste just like you're going to do on the exam. That was beautiful. You guys are awesome. I got to remember that when I meet with my kids tonight. You have 1:30 left. About a minute. There is a timer on the exam. You want to make sure that you pay really good attention to that timer. Don't turn the timer off. When the timer says your time is up, upload your response. You have 5 minutes. Don't keep working. Just stop mid-sentence. You probably finish your sentence, but you don't want to add any more. And you will definitely want to start trying to upload so that you have that entire 5 minutes. 5 minutes is given. It probably won't take long to upload. However, we have noticed that when students are uploading, if you're doing it using a PDF, or especially if you're doing pictures, it takes a while, and sometimes it says your response was not recorded. Please try again. If you try to trick the system and you're playing a game and you do, oh, I'm going to do with 1 second left, you're going to have an issue. So please, please, please follow the directions. All right, cool. So what I'm going to do is let's have you do your responses first. So if we can turn the chat back on, that would be awesome. And all right, go ahead and copy and paste your responses. Let's check and see. Awesome. Good. It's got a few responses here. We'll see if anybody else has any more responses. I've got David, Alan, Max. Good. Make sure you put your, make sure you put your reasoning. That's awesome. Good job. Those are looking good. Yeah, and remember, we always want to give the response. So answer the question, give your basic physics, cite evidence, and then draw a conclusion. So based on what I'm seeing, I think this is going to be nice. All right, we can pause that chat again. And then we'll actually go through the actual answer here. All right, thank you so much. The answer is E is the biggest. That's bigger than A, which is greater than D. That one's equal to F, which is greater than B, which is greater than C. So here we know that the work is equal to the energy stored in the block spring system. But they included mass. I would make sure that I say mass does not matter. And the reason you probably want to put that is because of the equation. So here's an instance where putting the equation in is a great idea. So US is equal to 1/2 kx squared. Now, knowing that you probably don't want to have to try to figure out how to do a subscript or superscript, you could just type capital U with a lowercase s equals 1/2 kx caret top 2. And that is absolutely fine. So the block mass doesn't matter. So notice that E has the biggest stretch and a larger spring constant. Next one, you'll see same type of thing, but just a little bit smaller. And then we keep going. Also notice that the stretch is squared. So it has a bigger impact than our spring constant does. So that would be the answer. Excellent job. All right, here we go. Next one. Another one where you're going to need to kind of make an assertion and then back it up. So we have two skaters, a small girl and a large boy. They're initially standing face to face, but then push off of each other. After they are no longer touching, the girl has more kinetic energy than the boy. There are 3 physics students. They make the following contentions about the forces of the boy and the girl that they exert on each other. So Ariana says, I think the boy pushed harder on the girl because he's bigger, so she ended up with more kinetic energy than he did. Boris, I disagree. They pushed equally hard on each other, but the girl moved further while they were pushing on each other, so she ended up with more kinetic energy. And then finally, Carmen says, I think the girl had to push harder to get the boy moving since he is bigger, but what caused her to accelerate more was that she recoiled. So they want to know which, if any, of these 3 students do you agree with? So you want to pick a student, that's your A, or your answer, and then briefly explain using B and C. If you don't want to use D on this one, you don't have to. This would probably be more of a briefly explain and not a full-fledged paragraph length response. That said, I'm going to give you about 1.5 minutes. And I'll call out every 30 seconds here how much time you have left. So you have 1 minute left. You have 30 seconds to answer your question. We have 12 minutes, and then we're going to take a little break, and then we'll flip on over. Peter will help you. About 10 seconds. And your time is up. All right. So I would love to open the chat again and then have those of you who have your answer with your reasoning, we'll have you put that into the chat. So we'll wait here just a second. Okay, what we'll do is we'll go ahead and go through the answer, and then maybe we'll have you paste your answers here. So for this one, Boris is the correct one. Why? Well, remember Newton's third law requires that they exert forces that are equal on each other, and notice that they're in contact for the same amount of time. But because the equal force on the smaller mass of the girl, that gives her a larger acceleration. The larger acceleration at the same time means she moves further, and the equal force applied through a larger distance means more work was done, and she ends up with more kinetic energy. So remember here, we're really looking at with work being the change in kinetic energy. And because she had more, she went from 0 to a lot, and the boy only went from a 0 to just a little bit because of his mass. All right, awesome. Here is another one. This one is various stacks of blocks. The masses are given in terms of m and the mass of the smallest block. Each block has the same height and has the same center of mass. So that's one thing we don't spend a lot of time on, but I think is pretty important, especially in projectile motion, which we really didn't do any of tonight, but that's okay. So each block has the same height and has the same center of mass. Consider the 0 point for the gravitational potential energy to be the height of the center of mass of the lowest block. So what we're going to do here is I want you to rank the gravitational potential energy of each stack. You could say that they are the same, and you could say that you can't determine them. But then you still need to explain your reasoning. All right, here we go. Go ahead, type up your answer. We'll give you 2 minutes to do that. So when you rank these, make sure that you give me basic physics. After you give me basic physics, cite some evidence. Tell us what you see in the picture that's going to help you back up your answer. And then draw that answer together in a statement. You have approximately 1 minute to finish this one. About 9 minutes till break. All right, you have 30 seconds left. Wrap up your answer. If you pretend it's like the exam, you'll know that when that buzzer gets to 0, you just want to stop what you're doing. Go ahead and get that pasted in. Make sure that it works well. You can clear your answer and repaste if you think that you need to make a change, but you cannot type in the box. All right, here we go. Let's check the answers, see how you did. So for this one, they are all the same. We know that potential energy is equal to mass times gravity times the change in position. And since all the stacks have the same mass and they all have the same center mass, they said that it is at the contact surface between the middle 2 blocks. Then since all the blocks have the same mg/y, they all have the same potential energy due to gravity. Very good. All right, so we're going to skip this one. That one's a little bit weird. I think we're going to skip this one too. And this one is a good one. Let's give you 2 minutes to do this one, since we're kind of shorter on time. In each one of these below, you have a toboggan. Toboggan is just a sled, and it slides without friction down a snowy hill. The toboggans are all identical, so they all have the same mass, And the starting heights, the vertical distance above the flat bottom of the incline, and the angles of all the hills are given. They want you to rank these on the basis of the speed of the toboggan at the bottom of the incline. And you will want to 100% make sure that you give me basic physics, cite evidence, draw it together after you give me your ranking. All right, here we go. 2 minutes, last question. About 40 seconds. Got about 20 seconds left. Ten seconds. All right, your time is up. Let us take a look at what you did and see how you did. All right, here we go. A, B, and D all are the same. They have the greatest speed, followed by E. And then you have, that's greater than C, which is then equal to F. So why is that? We know the conservation of energy says that kinetic plus potential equals kinetic final plus potential final. And the kinetic energy at the bottom will be 1 F mv squared. The initial potential energy is proportional to starting height. So when we look at this, the ones that have the biggest starting height will be the same. So we've got, let's see, A, B, and D are the same. And I think there is so A, B, and D are the same. Then you have E. Notice that E is 12 meters. And then finally we have C and F, which are both 10 meters. So we've related the greatest potential should have the biggest kinetic energy and speed at the bottom. So this is a simpler one to do, but I still think it's pretty good. So anyway, I think that is about that on that one. The only other thing that I think I want to go through here in the 2 minutes we have left is just showing you a few things about qualitative, quantitative translation. We'll do this really quick. I'm not going to show you all of these, but when you are doing a QQT, this is going to be your first question. It's the 25-minute question. You're going to work with what we call multiple representations. So earlier today, we did some graphs. In fact, we did a lot of graphs. There's motion diagrams, free body diagrams, energy and momentum representations. So you might see bar charts or circle graphs, and then diagrams and pictures. So please, 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 please recognize that you're going to see those, and they're going to have you talk about them both In words, you qualitatively and then quantitatively. So that's kind of what you'll see as it goes through. Sometimes they're going to have you make a prediction. They will have you evaluate. We've done that tonight. Derive equations is not supposed to be on this test. So you will not have where you're going to derive an equation for an Atwood's machine. You might need to do that on the side. However, you will not, okay? So that's kind of what you need to think about. Don't forget about graphing, how that works. Really important that you understand kind of how the graphs come through and that type of thing. But other than that, you all should be really good. I appreciate your attentiveness, your time. Thank you for hanging around if you were here for the whole 2.5 hours. Sorry about the very beginning. We had some technical issues, but we obviously worked through those. And I know Peter Apps is the man with the plan for the next 2.5 hours. And he will do really, really, really well. So we are going to now go ahead and take a break for about 5 minutes. And then we will have Peter on. So thank you guys so much for hanging out, and super good luck on the test. You guys, just based on some of the answers I've seen, you guys are going to rock this thing. So have an awesome time. Thank you, Tan, for having us do this. It was a ton of fun. See you, sir.
Thanks, Christian. Hey, Christian, would you mind sending us the slides and stuff so that we can send them out to the students? How's everybody doing, guys? Can you guys hear me? Hi, everybody. My name is Tan. I am the Chief Product Officer at Fiveable. Amanda's currently giving a pep talk to AP Chem right now because that stream is double this stream. Thank you so much to Christian Horner for doing the AP Physics CRAM finale. We will be posting the slides in just a moment. So just keep an eye out on your email for those resources. We'll also send you a bunch of different things that you can use for, such as like our AP Physics study plan, our Quizlet decks, all that stuff. Like I said, Amanda can't be here because she's currently in the other stream. But we will, I see some of you guys are asking about jobs. We will be hiring students over the summer and next school year. So if you pass your exams and do well, then you can apply to become a part of the Fiveable team. So right now we're just taking a break until Peter gets here. Peter is our head physics teacher. We'll be doing like actual FRQ practice. Hey, Peter.
Hey. How's
it going?
Oh, it's going well. Going well.
All right. It seems like the tech issues have smoothed out a bit. So I will let you kind of like introduce yourself. I don't want to stay here too long, but I think they need to hear a pep talk from you. So if you want to hop into that, feel free to.
I can try my best. So, okay. Thank you. All right. Hi, everybody. My name is Peter Apps. I am the CRAM Physics EP1 teacher, and this is my 15th year of teaching, give or take. The crazy part is we have more people in this stream than are in the entire high school that I teach at, which is kind of cool for me. I've never taught to a crowd this big, which is really, really awesome. So, all right. And I know you had some technical issues going on with stuff like that earlier. I'm having a small one. I can't see chat. So if you message something, Aaron or Jacob will get those messages to me. It just may be slightly delayed in that way.
But Hey, Peter, your camera's a little bit laggy.
Yeah, it kind of is.
Yeah.
So, I will see what I can do. I can't guarantee a fix for that.
You sound perfect, but I think your camera's a little crazy.
My camera's a little old too, so I have everything broke, so I'm kind of just stuck with what we have.
No worries. We should have better prepared you, but yeah, I think, yeah, guys, his camera it's fine. The stream will go fine. Like slides and FRQ stuff will be up on screen anyway, so it won't be anything.
I'm going to use my face pretty soon anyway, because you don't care about seeing me, you care about seeing the content. I'm going to disappear anyway.
Same.
Anyways, pep talk, stuff like that. This exam, you guys can all nail. It's 2 questions. And although that maybe seems scary that there's 2 questions, there's not that many options for what can be on those questions. Christian did a great job with energy and kinematics and forces and stuff like that. Those are the foundational building blocks. And I can guarantee you one of those FRQs, either the QQT or the paragraph length response, will be talking about energy. 100% guarantee we will see that sort of thing on there. So if you can get energy and then we can apply it well and do the BCDA format, it'll be good. It's a new experience for all of us doing this online. And I know some of you guys are stressed out about logins and uploading and stuff like that. Give yourself enough time. If you have issues, that's why they're doing a makeup one in June. I know that's not ideal, but there is that backup just in case all the tech decides to fail and stuff like that. But stay positive. We've got great resources here. And we got another 2.5 hours to go and get you guys prepped for everything and anything you need to do for this exam. So I'm going to get my face out of the way here, and we're going to go over to our slides and stuff like that. So hopefully this works. All right, so make that big, get me out of the way. All right, so Christian, as I said, he did a great job on 1 through 4. We are here to do the rest of it, 5, 6, 7, and a bunch of FRQ practice. For those of you who haven't streamed with me before, my style is slightly different. I'm going to do a ton of examples and kind of talk through the examples as we go. So instead of having slides about content, we're just going to kind of work our way through a ton of different examples on momentum, momentum, simple harmonic motion, and rotational motion. And then probably right around the 8:30 mark or so, we'll get into the actual most recent exams and tips, tricks, that sort of stuff like that. So momentum stuff, let's start there. Momentum is one of these conservation laws that we need to know. Super, super common. When Christian talked about doing basic physics concepts, that means it's either a Newton's law or it's some sort of conservation law. Those are the points that we're going to drive across here. And that's where we're going to be starting for all these things. So conservation of momentum, always, always, always super important to know how to do. And it's P before equals P after. When you start something, if you have momentum being conserved, it will be the same before and after. Now, how do we know when we have momentum being conserved? Well, that last bullet there, the speed of the center of mass, that's conservation of momentum. On there, it can only change when you have an external force on there. Okay, seeing in the chat here, they're asking questions about when do I use BCDA? Anytime it asks you to write. If you think that they're asking for an explanation and there's more than just a 1-sentence explanation, BCDA would be my recommendation. Definitely for the paragraph length response, QQT would be a good place to do it too. Again, if they're saying justify your response or in a longer explanation. If they say briefly explain, you don't need to go all the way into BCDA, but if they say anything more than briefly explain, justify it, paragraph length response, definitely stick with the BCDA. And we'll have a couple examples of that in a second. So conservation of momentum applies when we do not have external forces. So if we can define our system so that all of the forces that are going on are internal forces, like Newton's third law pairs between two things colliding together, we will get conservation of momentum applying. Okay. The other key buzzwords here, inelastic and elastic. Inelastic is when two things hit and stick together. That is only conserving momentum. But if the question mentions elastic in there, then you're going to have momentum and kinetic energy be conserved. So we can talk about P before equals P after and KE before equals KE after. And again, those are the total amounts in there. All right. This one is kind of the same sort of thing. Momentum, I couldn't tell if you guys wanted words or pictures, so we did both here. Momentum is the quantity of motion something has. The more momentum we have, the harder it is to stop something moving. We have two big kinds we're going to be dealing with that have conservation laws. We have linear momentum, P, and angular momentum, L. We'll get to angular momentum a little bit later in the talk when we do rotational motion, but that's also another momentum that can be conserved as well. And again, anytime we do not have external forces or external torques on our system, we will end up with momentum being conserved. Christian mentioned a lot of stuff about graphs too. Graph reading for this, we're going to deal with impulse and being our big graph reading skill for this. So if you're given a force time graph, the area under the curve is impulse. That is the change in momentum of the system or the object, whatever we're looking at here. Similar for that is J or I, depending on what your textbook says. I like J, I'm going to use J for that, but that is F delta T. And that is also on your reference tables in there. Okay, so let's jump into a couple examples here. We're going to start pretty simple. If you guys want to, I'm going to put a timer up or try to put a timer up like Christian did. Give you guys a couple minutes to try to plan out your response to this, and then we'll throw up the answer and then discuss. All right, so question number one. We have a track consisting of a frictionless arc XY, which is a quarter of a circle of radius R, and has a rough section between Y and Z where the kinetic coefficient of friction is mu. Both blocks, block A and block B, have mass big M, and a student's going to let block A slide down that ramp, and it's going to collide instantaneously and inelastically with block B at point Y. The two blocks move together to the right, sliding to point P, which is the distance L from point Y. So the blocks are going to drop, they're going to slide down that ramp, they're going to hit and collide inelastically, meaning they stick together, and they're going to slide. The student has two extra blocks, both of mass 1/2 m, that they're going to be able to add to either block A, block B, or both. One on block A, or both on block A, both on block B, or one on each. If you want to have the combined blocks slide the furthest they can, how should you add them? And then briefly explain without manipulating equations. So this is not a BCDA. Briefly just means here's the basic answer and why. I think about 2 minutes for that should be good. So I'm going to give you guys 2 minutes as I try to move this out of the screen here. And I clicked the wrong thing. So go ahead and answer that. And then we will take a look at my answer when you're done. Okay. So this would be a good time, again, to practice. If you want to paste something in the chat, if you want to go through, practice that copy paste sort of thing. Or if you want to try handwriting it, photoing, that's fine too. Practice the way you're going to do it on the exam, preferably copy paste. Okay. All right, another 40 seconds or so. Go ahead, think out your response, and then we'll try to tackle it here. Wish I could see the chat, but oh well, it works. Again, thinking about what physics principle you can bring in, what evidence can you put into the chat or bring from the problem. We're not looking for a whole BCDA, but it doesn't hurt to think about it in those sort of terms. All right, and there it is. Wow, it rings pretty loudly. Okay, so there is that. Let's see how you guys did here. Let's work. Okay, so here is my take on it. The correct answer here is adding both masses to block A will result in the blocks going further. So that should be the box we checked there. We want to have more momentum before the collision. And the more momentum we have before the collision results in more momentum after the collision. And that makes it have greater velocity afterwards, which means they're going to travel further. Okay. Now, this question, if it did say, justify your response or something like that, then I would go into a BCDA sort of thing. Conservation of momentum is our big point here. You also could have brought in conservation of energy for this, because we're talking about going from point X to point Y, potential energy turning into kinetic energy. We can make it work that way too. But that's more than this question needs. For that, just sticking with, hey, P before equals P after. We're conserving momentum. More momentum we have beforehand means more momentum afterwards. And then we're going to get a collision going through and transferring that. All right. So that is the first question. Let's see if we can get to the second one here. So the second part, normally what this would be is some sort of, don't hit the wrong button. Some sort of derive an equation part. But because on this year's exam, we're not really deriving much, we're going to stick with the other way of talking about quantitative sort of stuff, and that is explaining an equation. So we have that student, some magical student that we're talking about here, is told that this equation is valid for finding V after the blocks collide. Okay, MVA plus 3MVB over 3M equals VC. Whether or not this question is, or this equation is correct, does it agree with what we thought about in part A? In other words, does the equation for VC have this expected dependence that you reasoned for in part A? Briefly explain, without deriving an equation, not doing any math, no equation shown, simply yes or no, and an explanation why. This sort of thing, I'm thinking it's about a 1 minute sort of thing. So let's try a 1 minute task on that. Let's see, 1 minute. Start. Okay, so I'll leave that sitting out here. So again, same sort of thing. Is this going to, does this equation match our reasoning that we had in part A? Yes or no? Okay, and we've got a ding there too. Stop. All right, maybe I'm going to put that away and just do a manual timer. All right, let's check out this one here. This one, yes, it does. This works really well. It's not perfect. We're not saying this equation is the correct equation, but it does show the right relationship. In part A, we said that if you were to add the mass to block A, you'll make the block go faster and farther. Well, MA happens to be in the numerator of our equation. So if I increase that MA, then the numerator gets bigger and the whole fraction gets bigger, and therefore the velocity is bigger. So that relationship does work. And that's really all we need to say here. It's not asking for a crazy, long, detailed explanation. They just simply want to know when they read through this question, when we as a reader score this, we want to see, did you get the relationship right? Now, this is a great example of you're not going to be double penalized for anything. So let's say, for whatever reason, you chose to say that we were going to do both blocks on B in that part A. Then your answer could also still be, hey, yes, we're going to make MB get bigger, so bigger masses will mean bigger velocities. Or if you said one of each, that's perfectly fine. The scoring guide for this part of the question will definitely talk about, did you use your explanation match up with your answer to part A? So you're not going to get double penalized for messing something on part A and then doing it correct, using that part correctly in part B. So don't worry about, well, if we're stacking all these questions together, does that mean I'm going to, if I make one mistake, I lose the whole thing? No. This is all about, can you use the information that you're given correctly? And in this case for part B, if you said something wrong for part A, it still carries through perfectly fine with that. So we are looking at that being nice and organized there. All right. Okay, part C. This is the last part. Actually, this is kind of hard to read. Let's go back here. Part C, that's a little better. Now, for this one, we're going to assume that the students modified everything. They did everything correctly to get the blocks to travel as far as they can along the flat part of the track. They released block A, and they predicted, they calculated out to say that, hey, the block should go a certain distance, but it doesn't. It goes a shorter distance. Possible reason for why those blocks did not travel as far as anticipated after you increased the mass of the block. So we say, hey, we doubled the mass of A. Great. It should go twice as far, and it ends up going 1.5 times as far, or something like that. What's a possible reason for why that could happen? Okay. Think about this one for a minute. I'm going to keep a timer off to the side here, so it's not going to ring like crazy. We'll give you guys about a minute or so. Just brainstorm. What are some possible explanations for why this one could happen? All right. All right, another 20 seconds or so. All right. So let's see how this one did with that. Boom, boom, boom. Okay, so best answer for this is that there was inelastic collision. The question told us that this collides inelastically. The blocks stick together. Because they're sticking together, we know for a fact that we are going to lose some kinetic energy. We're not going to have the same energy before the collision that we do afterwards. We lose some kinetic. And because we're losing kinetic, we will lose our velocity. We will have less velocity than we would have predicted if this was elastic. Okay, this is, if somebody's on this, please stop trying to draw on the stuff. That's going to be really annoying throughout that. So we may have to change off of this to something else then. So we're going to get less kinetic energy as a result of that. Okay, and that's the best answer for that. If there was a different one, we could go other possibilities. It's kind of tough. We have friction on the track. You could say maybe something like, I guess, yeah, let's put another example on there that could work here. Another option. The other option here would be to do something like that. And again, that's not a complete sentence. Please don't think that that's an acceptable answer. But this is the other option I just thought of and didn't write down already. So because you have a larger total mass, because you added the blocks together, you added those extra masses on there, you have now 3m of mass, which means the air force of friction is going to be bigger. FF equals mu Fn. Bigger Fn, because of bigger mass, means more force of friction. And that means the work taking that energy away from the block to bring it to a stop, must be less than the energy there. Okay. All right, and this is looking pretty frustrating. So I think I'm going to close out this. We're not going to use this anymore because people are jumping in and doing stupid stuff. So thank you for ruining that, whoever that was. So we're going to go back to doing this kind of old school. I will just type in responses as we get there. So someone is asking why kinetic energy is lost at all. So thanks, Jake. In this situation, in an inelastic collision, when the two blocks come together, they don't conserve their kinetic energy. They're going to lose kinetic energy, and the energy gets converted into thermal or sound or something like that. If you can imagine like a car crash, two cars coming together and they crash and the wreckage locks together, all that energy, some of that energy goes into deforming the metal, goes into crumpling it, goes into heating up certain parts or sound or stuff like that in there. So that is why you can lose some kinetic energy in that case. We still conserve momentum in all these cases because the force that's doing that, that's converting kinetic energy to other kinds of energy, is internal. It is caused by one object smashing into the other. It's a Newton's third law pair. So the two-car system doesn't have a loss in momentum. It has the same momentum before and after. It also has the same total energy before and after, but it doesn't have the same kinetic energy before and after. Okay, so in this case, if we're talking about a collision, we are talking about kinetic energy, or sorry, total energy and total momentum, both being conserved. So all the potential energy we started with at point A will also be the same total energy we have at the end. It just won't all be kinetic. It'll get converted into some other kind of energy with that. So hopefully that makes sense in there. Okay, let's try a different one here. Okay, well, let's take a look at this one. This is the common sort of thing here with the arguing students. I'm going to create a poll here. We'll just let you guys choose some answers here. I'm going to abbreviate names, so A, B, C, and none. So let's have you guys go ahead and answer the poll here. We've got two identical carts traveling in opposite speeds, are shown just before they collide. The carts carry different loads and are traveling at different speeds, and the carts stick together after the collision. So they're going to go stick afterwards. Alex says the carts will be at rest after the collision since the initial momentum was zero. Therefore, the final momentum is going to be zero as well. Belinda says if that was true, that means you have no kinetic energy after the collision, and that violates conservation of energy. Since the right-hand cart has more kinetic energy, the combined carts will be moving slowly to the left after the collision. I also think the collision pairs of carts will be traveling left. Conservation of momentum and energy are both satisfied. All right, who is right in this case? Take a minute, vote, and then the other part would be, I can't have you guys put in your reasoning here, but this is where I would say is a part where you're going to be able to explain your reasoning in there. Okay, so let's see if this works now. Okay, so at this point in time, we've got a good number of votes in here. And the trend is going in the right direction. So correct answer here, whoa. Correct answer is Alex is correct. I'm not sure if can I do this and edit this while I'm presenting? That's a new question. Not really. That's awesome. Okay, so you can't see the response. Alex is correct here. This is a conservation of momentum. The question specifically says that the cars stick together after the collision. Because they are sticking together, they will not have the same kinetic energy after the collision that they do before. Sticking together is a guaranteed inelastic collision. Okay, so because we are sticking, that is guaranteed to be inelastic. Okay, Belinda is almost true, but zero kinetic energy doesn't violate conservation of energy. Conservation of energy is potential and kinetic and all the other types that we talk about here. So you're not violating conservation of energy here. You're just converting kinetic energy into something else. And because you're converting it into something else, there's no violation law there or anything like that. What the heck is going on here? Okay, so that's kind of where we're going with this. With there, A is definitely right. Good job to those of you who chose A. All right, this next one is one that, let's see, am I comfortable enough trying to put that back on? Probably not, but let's see. Let's try to switch back over and we'll go through this part line by line because this one is where I'm looking at doing a ton in here. So hopefully we can make this work. All right. So we'll see if this works here. Because I do want to take this and document the kind of line by line process for this one here. So this one is a student's testing throwing a dart at a block of mass M, as shown to the right. When struck head on by the dart, the block swings up and goes up to some angle theta max. Now the students got 3 different options of how they're going to throw these darts. They're going to make it so that it throws up and sticks, up and bounces, and then up and goes right through the block. So you're going to have basically one case where this thing will stay embedded in it, one where the dart goes all the way through, and one where the dart goes backwards. Out of those 3, which one is going to give you the highest angle that you reach? All right, so if I'm thinking about this, paragraph length response, let's kind of go step by step through this. So I want to start with B, then C, then D, and then A as my general outline here. With this, basic physics. Okay, in this question, they're talking about collisions. Collisions should involve some momentum. And because they're talking about the block swinging up, that's also energy. Okay, this is ridiculous. Okay. So I guess, you know what? We're going to change again. We'll do this way. Okay. So let's put this up here. And you guys can't get to this, so that'll be fine. So B, C, D, A. All right. So basic stuff, we're looking at momentum and energy. I have to bring in conservation of momentum, and I've got to bring in conservation of energy to this question. Okay. Claims. What are we claiming? What are we citing here? That stuff is going to really depend on, come on. There we go. Sorry about this. I should know better than trust kids with technology, but so we're talking about different angles. We're talking about going from having kinetic energy at the bottom to potential energy as it swings up. So conservation of energy as well. Info. Oh, we're throwing all the darts at the same speed. So we're going to look for something like a bigger change in momentum of the dart leads to more kinetic energy. And then that's kind of my claims and stuff like that. We're going to flesh it out in a second here. So for starting this, we're going to start with by saying in this situation, there is conservation of momentum. And so I'm kind of going through, we're talking about our system. Good thing to do here, especially in a paragraph length response, being clear about what your system is going to save you a lot of time when it comes to and what types of energy do we have, that sort of stuff like that going on. So in this case, we have conservation of momentum and energy in this dart block Earth system. The dart transfers momentum to the block. I'm going to read it. Let's call it KE. So that's kind of where we're looking here. So defining just facts from the system. We're talking about the dart's going to hit it. It's going to give it some momentum. That momentum is going to make the block have kinetic energy and swing upwards to potential energy. I don't feel like writing that. So something like that is where I'm going. We're trying to hit all the key parts here. Conserving momentum, conserving energy. Start off with your fundamental basic ideas. Define your system, and then start with what's going on. So this isn't perfect, but it should get all the points. The parts I would flesh out if I didn't want to move on to the next question and stuff like that. Is all this chunk writing here. The question I'm asking as a reader now is, okay, why does that have the greatest change in momentum? So maybe saying something about because its direction changed, et cetera, et cetera, et cetera. The bounce, it doesn't matter if it's elastic or not. It's simply because the momentum goes from being in the positive direction to the negative direction. So if I wanted to say we have let's say our velocity was 5 meters per second and then turned into -5, maybe -4 or 3, I can type, right? Meters per second. That's a change in 8, right? Okay. If we go let's say it passes right through, that would be going from 5 meters per second to 4. Well, that's only a change of 1. Right. That's a very, very small change in the dart's velocity and momentum. If it keeps going right through, that dart keeps its momentum going in the forward direction. And as we go through that way, we will see a smaller change. So the biggest possible change you can get is when it's changing, going from +5 all the way to 0, and then backwards in the other direction like that. That's what's going to give you the best outcome and the biggest change in momentum for that. Yes, if the dart were to bounce off, it does have to stop moving at some point in time and then gets propelled back in the opposite direction. Just like a ball you drop will stop going up and down at the lowest point. It'll stop moving and then fling back up. Same thing happens with the ball going sideways in there. All right, I'm going to keep that off to the side here now because I have a feeling we're going to need that again. And I'm sorry again for doing it this way, but I'll have to find something better for next time. Okay, so that's momentum. Momentum, if I want to talk big picture exam sort of questions, I don't see momentum being a huge, super common question on this year's AP exam. I'm not saying don't study it. I'm not saying don't know it, but I'm not seeing it as a red light flashing, guaranteed to be on the exam sort of topic. I see energy being that way. I don't see momentum being that way. Okay, so know it. Know when you need to apply it. Anytime we're talking about a collision, stuff sticking together, hitting, bouncing, stuff like that, momentum's going to show up there. But I can't guarantee that it's going to be on there, and it's not even super likely that it's going to be on there either. So I would say try to stay away from stressing out about momentum. If you want to stress out about stuff, spend your time studying energy, spend your time studying forces, rotation, simple harmonic motion. Those are the ones that I would say are going to be the big ticket items on there. All right, speaking of our next big ticket item, simple harmonic motion. This one is a great FRQ question topic, because when you're talking about a pendulum or a spring, you automatically can bring in energy. You can automatically bring in forces. You can do acceleration graphs. You can do velocity graphs. You can do all these different parts to it, which means that if I were to bet money on what's going to show up on the exam for a free response question, paragraph length response, or QQT, I would be very surprised if we did not see some sort of spring or pendulum sort of question. Can't guarantee it. I didn't write the exam, but I'd be very surprised if we didn't see one of those things. Okay. So stuff we need to know for simple harmonic motion. We need to know we've got 2 equations for periods, time for one cycle, going back and forth through there, one for a pendulum, one for a spring. Please don't get them confused. We also have energy for a spring, 1/2 kx squared. We've got Hooke's law for forces in a spring. For pendulums, we've got free body diagrams. Some component of gravity is always going to be providing the force or tension in the string. And then potential energy is gravitational, MGH. So that's where that's coming from there. So we're going to be asking questions like, when do we have the force be the biggest? When do we have the force be the smallest? Well, excuse me. When's our acceleration the biggest? When is it the least? Velocity, greatest, least, and stuff like that. And we always have to have some sort of restoring force going on here. Some force that is always pulling our object back towards its equilibrium point. And equilibrium point for the spring is when x equals 0. And for a pendulum, it's the lowest point in that swing. It's where it would be naturally want to go to on there. Okay. Now, so how does this work for pendulums? Well, you've got some component of the weight. This mg sine theta part is what's pulling our mass back towards equilibrium. Also to point out, I don't think it's going to be a big deal for this exam, but this pendulum equation only applies when the angle is very small. Like if you're pulling this back a small theta, this equation will hold. If it is much bigger than that, then it will not hold. So if you get a question, and again, I'm not expecting one, this is kind of out there, But if you do get a question that talks about the angle of a pendulum being 90 degrees, and somebody is saying, well, why doesn't the period of a pendulum equation work? It doesn't work because that equation is assuming the angle is very small. Okay. We also have for a spring, you guys have seen this part. This is the mass on a spring. If you're tracking it out, it behaves like a sine wave, which means you can use the wavelength, the distance between two crests or two troughs, to figure out the period. Period is 1 over the frequency. Most of the time when I've seen questions like this, we've talked about period. I'm not expecting a crazy screwball sort of thing where they say how to suddenly switch to frequency, but it could happen. We might get one like that, but I'm expecting it to be period, and I'm not expecting any crazy stuff to go on here. What I'm expecting are a lot more questions, kind of like this one. Okay. And I was worried. I was watching the stream earlier, and Christian almost stole this question. Okay, thanks, Aaron. So sorry, go back a step here. When we say small angle, if it's, I would say personally, if I would have my kids do it in a lab, less than a 20-degree angle works great for this. When you start getting to 45, 60, 80, 90 degrees, that's not a small angle anymore. It's one of those where we kind of fuzz it a little bit. I don't think there's a hard and fast number that says when this angle becomes bigger than this, it's not considered to work anymore, but keeping it small-ish. So 5 degrees, 10 degrees, 15 degrees. That's what I'm saying when I mean small angle. And I think if you were to ask a question on this sort of thing about whether the angle is too big or not, you can simply say, if this applies for small angles, and if they increase it to a large angle, and they would have to exaggerate this a bit, 90 degrees, 95 degrees, 80 degrees, something like that, is when it won't hold true. Okay, so we're trying to keep it in the small range, 5 degrees, 10 degrees, 20 degrees. Normally that comes into play more if you're asked to design an experiment, but I don't see us designing an experiment in this year's exam. So it's one of those, I mentioned it just because it might show up, but I'm not saying that you need to know that fact or memorize that fact or anything like that. It's simply just in case it does. All right, let's take a few minutes here and have you guys plan out and solve this question. All right, so I'm going to give you guys 3 minutes for this, and I want you guys to really take some time and type out the explain your reasoning part for it. Do that practice, type it out on docs or write it on a sheet of paper or something like that, and then paste it into the chat or something along those lines when we are done. So I'm going to give you guys 3 minutes to rank them. Which period is the greatest? Explain why. All right. So let's go through. In this case, oops, wrong way. Just end up with something like this sort of logic. Okay. Also, if you feel the urge to write out your stuff, your equations, something you want to handwrite them because you've got equations, this is perfectly fine for how we can write equations in a Word doc or a Google Doc. Anybody who's reading this, who's studied physics, will know you're talking about the equation off the reference table. And we are not going to be super picky about your formatting and stuff like that. So SQRT for square root, perfect. If you want to do the check mark option or something like that, or raise it to the 1/2 power, that's also fine in there. So reasoning here, if we make m get bigger, my period gets bigger. If we make k get smaller, my period gets bigger. The fraction that is inside the square root, m over k, is what's going to determine, relatively speaking, the period of motion. So we have, in this case, A will be 1/5. B will be 2/5. Well, 2/5 is bigger than 1/5, so B has to be bigger than A. And I screwed up. Oh, goodness. Terrible me. Terrible me. Please yell at me in the chat. This is not correct. Put that in there. This is what happens when I can't use my primary source. All right. So we've got C bigger than D, or C equal to D. The reason for that, they have the same ratio here. 1/1 for C, 4/4 for D. It's the same ratio. They are 1 on there. And then B and A happens to be 1/5. And C will be, I don't know why did that suddenly happen. There you go. Okay. On there. So we're looking at that different fractions in there. This is also a great one. You guys are allowed a calculator for this exam. So let's use it and actually crunch the numbers before you solve it. This says explain your reasoning. It's also perfectly fine to say, hey, if you plug all the numbers into the period of a spring equation, it comes out to be A is such a number and B is such a number, D is such a number, stuff like that. Therefore, A is that sort of thing is perfectly fine to do for that sort of thing as well. Okay, so you can crunch numbers, although it's one of those, I'm not expecting you to actually get numbers for these questions. I would much rather expect something where you have 0 numbers and just symbols, K's and M's, and in this case, A's for amplitude. The interesting part here is that amplitude does not show up anywhere in the period of a spring equation. So it doesn't matter. Okay, you could stretch this 5 meters long and it won't change the period, the time it takes for one of those motions, because the period for a spring only depends on the mass and the spring constant. All right, next one. I'm going to do another poll for this one. So we have a mass oscillating up and down at the end of a spring, and we have 3 students, A, B, C, or D. So again, who do you agree with? A, B, and C, or none? All right, so add that in there. Okay, so there's the poll on there. Who do you agree with? Mass oscillating up and down in the spring. Take a couple minutes, and again, we're going to say who's right, who is wrong, and then why. Why is the key part here with that. So as you guys are voting, I'm seeing 2 clusters of votes, which is not bad, on there. Let's take another minute or so, and I'm going to start typing out my response. So at this point, I think, yeah, it looks like votes are kind of stabilizing here. We're kind of a little bit all over the place, but let's talk about what's going on here. So in this case, student A is the correct person. The acceleration is the largest when it's at the end of its oscillation turning around. So Eileen, I'm guessing that's how you say it, will be right. The reason for this is Newton's second law, F equals ma. Okay? In this case, there's two forces. You have gravity acting downwards on the mass, and you have the spring pulling upwards. When you get the largest net force in there, you will end up with the biggest acceleration. So in this case, because in this particular arrangement, to talk about the lowest point, force on a spring is pulling it upwards, gravity is pulling it downwards, that is your net force. When you make this Fs as big as possible, making x as big as possible, you will get the biggest acceleration out of it. Bridget is getting confused here. Acceleration does not mean velocity. Yes, it is stopped there. Yes, the mass is not moving at that point. But if there wasn't an acceleration, if acceleration was 0 at that extreme, it wouldn't come back. It would have no velocity and no acceleration. It would just sit there at the lowest point. It would be fully extended, just sitting right there. That is not what we see happen. That spring is going to oscillate. It's going to go up and down and up and down and up and down all throughout there. Okay, and Chandra is sort of right and sort of wrong. Its speed is changing the most, not at that point. If you were to look at a graph of this, you'd see it act very much like a sine wave, where the velocity is at its maximum halfway through. This is where its velocity is the maximum, but the change in it isn't where it's changed the most here, not at this point. This is max velocity, max kinetic energy, stuff like that. Extreme is where you have max acceleration, max force. All right. So those of you who said A, good job. Those of you who said C, we need to bone up a little bit on simple harmonic motion there. Okay, and now I'm sure you guys have seen this question already. This one, I'm putting it on because it is the latest and greatest FRQ question out of College Board. This is the sort of question that you can definitely expect to see on your exam. Okay. We have multiple different objects. We have different systems going on here, and we want to see what's happening to the energy. Is it increasing, decreasing, or constant for each of the systems below, and explain why. All right, so let's stagger this. Let's give you guys, I'm going to say 3 minutes or so. And I want you guys to take some time and just think about, I'm not going to get into explanation yet, but just for A, B, and C, is the energy going to increase, decrease, or remain constant for that? And then, you know, I think I'm going to write right on here, just to make it easier. You guys don't mind this. This way, all the answers are here, and I won't have to rewrite them all, which seems to make sense. Get the right font here. Okay, so unstretched length L, hung vertically, going through there and stuff like that. How do we make it so that we have the energy for system A? Okay. Okay, that's a little bigger. All right, so let's start going through this. And I probably really shortchanged that few minutes there. That's okay. So systems energy, blah 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 blah. All right, so system one's energy. I wish I could see it in the chat what you guys were saying, but I can't because my chat isn't loading. So hopefully you guys are all saying that system one's energy is increasing. Okay, now, why? And here is the key points to this year's AP question. They care a ton about the why. Okay, being able to explain and justify your answers is the key idea behind this year's exam. Okay, being able to logically and consistently talk about it. So let's go through this. System one's energy. Well, system one is just the block, right? So if we talk about this, we only have the block. If I only have the block, that means I can't have any PEG or PES. I can't have any potential energy due to gravity because the Earth isn't part of my system. And I cannot have any potential energy in a spring because the spring is not part of my system. The only type of energy I can have is kinetic energy. And because as the block goes from the lowest point upwards towards equilibrium, we know velocity is increasing. And that's system one. We can't use PEG because we don't have the Earth. We can't use PES because we don't have the spring. Okay. Another way to think about this, just to bring in another perspective here. This is the other way to think about it. If you're doing a system, the energy of a system will change if and only if there is an outside, external, not part of the system, force acting on it. And in this case, the force on a spring and gravity are both external forces. Force on a spring pulling upwards is bigger than gravity because we are accelerating upwards, and we're doing positive work on the system. Okay, that's system one. System two, this one, believe it or not, is decreasing. In this system, we have PES because we have the spring, and we have kinetic energy. Okay, but that's it. We don't have potential energy due to gravity because we're not including the Earth in this system. I know I'm harping on it. This is kind of important here. Yes. So for system one, I definitely can use work to explain the increase in energy. No problem there. For system two, I'm going to use work to explain the decreasing energy. Okay. This one is a little bit tougher to do, talking about types of energies, because you could, but not talking about gravity and stuff like that makes it kind of difficult for this. What I'm going to do for this is say system two has a net downwards external force, gravity, So using work for this one, for part B, the system 2, the forces that are not part of this spring and block, the only force on there is gravity. That is our outside force. Gravity is acting downwards. That is the opposite direction of our motion, which means it does negative work. It takes away energy from the system. And that's why our energy is decreasing. Okay. I cannot include in part B, I cannot include the force from the spring because that is an internal force, not an external force. Okay. We can only include those external forces throughout that. Okay. So closed and open systems, that's a good topic to jump into right now. A closed system is one where you have everything included. You have no external forces acting on a closed system. So for example, system 3, where we include the spring, the block, and the earth, or sorry, just the block and the earth without the spring, we are talking about energy. If we include everything, the spring, the block, and the earth, everything put together, that is a closed system. The block and the earth system in 3 is going to increase. Okay? This is increasing for the similar reasons here. We have an unbalanced outside force. This is the spring again, because the spring is not part of the block and earth system. Unbalanced outside force, doing positive work. And if you can imagine if we had a system 4 that was the spring, the block, and the earth, that's the closed one. Every single one of these systems here, 1, 2, and 3, they are all open because they all have some outside force acting on them. In A's case, it's upwards. In B's case, it's downwards. In C's case, it's upwards again. So we are talking about that sort of difference going on there. All right. Next part. Okay. And this is getting into the idea. I know most of you guys have seen this question before. This gets into the idea where we have multiple representations of stuff and also multiple topics pulled in. All right, question from the chat here. Would I get points for saying that work equals force times distance and the upward spring force decreases for B? Work equals force times distance, the upward spring force for part B in there? No, because part B, you can't talk about the spring force and there because the spring force is part of that system. The force you can talk about when doing work for part B or system 2 is gravity, or is the weight of the object. And the weight of the object, constant and downwards, will be the one that's going to result in the outcome for that. For part C, you can talk about that the work is done a large amount at the beginning as that force gets really big and then decreases, goes upwards. So part C, you could talk about that, but you don't need to. And if you're given the option to not have to say something, don't say it. Answer the question, answer it fully, but don't go beyond. Don't offer other parts of information that might be useful or might not be useful. It's not needed in that sort of chunk there. Okay, part D. The block is released at time t equals 0. The length of the spring is shown in the graph above, during which intervals, if any, is the weight force acting on the block greater than the spring force acting on the block. So when is mg greater than the force of a spring going up? All right. So this would be lowest point, highest point, lowest point again. So where on there would the weight be greater than the spring force? Any point where we have a concave up curve. Okay. L, this is a distance or position time graph. I know it doesn't look like one, but it is. And a position time graph, just as a couple little tips and tricks here, a position time graph, I think Christian went over these already. Concave up is, yeah, positive. So actually, for the question here, we're pulling it down to L3. Yeah, so they're calling this upward. So up is negative in this case. Basically, it's where the concavity changes. So it's from about this point, this T1 quarter to T3 quarters. We will have the force on the spring less than the force from the block. This is where the spring is compressing, getting back to its natural length. And that's where X is small enough that it's not going to make a difference. Okay. And part E, we add a new block. That new block of mass M is going to change to a bigger M. That bigger M is now going to cause some changes here. What's going to happen? How will this graph change? All right, well, the graph's going to change in two ways. We're going to have a change because the mass changed. We're going to have a change because the energy changed. So in this case, we've got the mass getting bigger. Well, mass getting bigger, if I go back to my equations here, the mass of a pendulum, bigger mass, means bigger period. So on this graph, I would see this whole thing stretch out. It would take longer to reach T. And because of that, we will get a stretched out graph. This graph will also be shorter. It's going to be shorter because we have added more mass, which means we have now suddenly shifted our equilibrium point downwards more and more and more. Because it's shifted down more, we don't have a nice, easy way to get that in there. All right, we don't have, I'm babbling. This is not good. Let me see if I can get a piece of paper and I will try to fix this for us here. I'm going to X out of this. So my apologies for a second. All these technical things are really flustering me right now, and I apologize to you guys for that. Let me see if I can make this work. So I'm going to stop sharing this. All right. Ay, 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 ay. Ay, 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 ay. All right, there we go. Okay, now can I share? Where am I? Share a screen. I want to share just this tab so no one else can jump on it. Okay, so in this case, what we're talking about here, we've got our spring with our mass. And as this goes down, we suddenly increase to a bigger mass at the lowest possible point. Well, what does that mass change? This would change, the force on a spring would have to get bigger. No, sorry, this changes the weight. So now we have mg going up. We have increased the weight at the lowest point, which means if our equilibrium point was here when Fs equals mg, that new equilibrium point is now significantly lower. It is down here. This is our new equilibrium point, which means our amplitude, our distance from our equilibrium point to the lowest point, is also less than it was before. We've gone from having an amplitude that is fairly large to an amplitude that's very small. So what we would see is our graph, instead of being this very nice elongated shape, is now suddenly becoming shorter and longer. So we'll see something like maybe something like that, where it takes a lot longer to reach our new equilibrium position. Okay. So 2 parts to this. We know period of a spring, 2 pi square root m over k. Bigger M means bigger period. That's why we stretched it out. Bigger M means new equilibrium position, meaning closer to our max length, smaller amplitude. That's why we shrunk the height of this. So our amplitude is much smaller than the amplitude was before. So those 2 parts for that. And they're asking for clear, coherent paragraph length response. They're asking for bring in the physics, come up with the idea, and then work through BCAD, basic physics, cite evidence, describe it. And then this one definitely wants a part. They want an application or a answer to that question because they did actually want that described in there. So for that, your B, equilibrium point, Fs equals mg, shifting to a new spot. Basic physics, period of a spring, 2 pi squared m over k. Citing evidence, bigger mass, and bigger mass means more weight. Drawing it together, bigger mass means bigger period because T is proportional to the square root of m. Bigger mass means our equilibrium position where the force on a spring equals mg is now shifted downwards, so we are closer to that starting point. Therefore, the graph gets stretched out because it takes longer to complete one cycle. So you will see T be a longer time, T new being greater than the T, and the amplitude becomes shorter because you are seeing that the motion in there. Okay, people are confused by this drawing. Okay, let's see if I can fix that. I can't because I can't just, hold on. Okay, let's see. I can grab and cheat and stuff like that. Okay, I'm going to grab, where's my snipping tool? New tool. Give me this. Copy this. Once again, my apologies for the crappy tech stuff here. Okay, so there's that one. And then there is this one. Okay, so there are the two parts that we have to deal with here. We have the graph beforehand and the positions here. So what happens if I add a bigger mass to this? Okay. Right now, figure 2 is showing our equilibrium position. This point right here is when we have the force on a spring going upwards being equal to the weight going downwards. Those two things perfectly balanced. Okay. L3 now, what we're doing here is we are grabbing a bigger mass. Well, a bigger mass means that mg is bigger. So I have a much larger downward force now with big mg. That means I need a much bigger upwards force with a bigger Fs to balance that out. Fs equals Kx. Okay, I haven't changed the spring at all. All I have done is said, oh, we have said that the spring is now stretched more. We got to get a bigger force. The only way to do this is to make X bigger. X is the distance between my equilibrium length, L1, or sorry, my unstretched length, L1, and my new part. So this is my X. X gets bigger in order for that to happen. That means that where this thing is oscillating from, sine waving around, is now shifted down from where it was before. It was here. Now we've shifted it to somewhere down here. So as this block wiggles, it doesn't go as high and it doesn't go as low. It's still oscillating about a new equilibrium position. So that new equilibrium position is going to be much closer to L2 than it is to L1. So we're going to see maybe this line on that graph is what I'm going to be drawing around and drawing some sort of sine wave over there. Okay. The amplitude gets shorter because we shift our balance point, our equilibrium position downwards. The other part, why does this stretch out? Period of a spring, 2 pi square root m over k. As m gets bigger, and we just added a bunch more m to our spring, m goes up. That means the period also goes up. The period is the time for one full cycle. So this will not take and not end at t anymore. It will have to end somewhere beyond the graph, someplace newer, further along than it was before. So because of that, our graph is going to look like something like this. It's going to take longer to complete a cycle, but not go as far down. So same sort of shape, but be stretched out much farther. So instead of having the lowest point at T1/2, its lowest point is now somewhere to the right side of it, somewhere on this side over here. With that, we can't tell for sure. We can't say it's double or triple or anything like that because we don't know. All we were told is it's a bigger mass, so it's got to be somewhere to the right. The shape should stay roughly the same, but it should be shorter because we now have a smaller amplitude because we shifted that equilibrium position down more. All right. Hopefully that helped. Hopefully that was a good sort of part there. Okay. Now let's do the next part here. Yeah, I've got more spring stuff. I feel like, you know what, we've got an hour left or so. I'm going to jump into rotational motion because I think looking at the questions that were asked, you guys want to spend a lot of time on this, and I completely agree. Let's spend a lot of time on that rotational motion part. Why can I not share my screen? So let's jump over to the finale here and present that. Okay, so let's go through to rotational motion. Okay, so rotational motion. Some of you guys who've attended the other CRAM sessions have asked for a cheat sheet or stuff you absolutely need to know, jot down on a piece of paper, sort of stuff like that, that is really, really important for knowing how to do this sort of stuff. Rotational kinematics is one of those that is going to have a lot on that cheat sheet. Not because it's super different, it's just all different symbols. All the concepts, though, everything we're to talk about from here until 9 o'clock is exactly the same as what Christian went over when we were talking about accelerations and forces and momentum and stuff like that. It's the same basic idea. We just have slightly different terms we're using for things. Okay, so just like with kinematics, you've got your big three equations: your V equals V naught plus AT, your X equals X naught plus V naught T plus 1/2 AT squared. You have the same exact thing for rotation stuff. You've got omega equals omega naught plus AT, velocity changes, theta ones, distance changes. Velocity changes when you don't know time. But the one thing you absolutely, positively, 1000% need to know is this first bullet point. Converting between rotational terms, A, or alpha, and linear terms, A. Rotational term, linear term. Rotational term, linear term. All that stuff is what you absolutely, positively need to know. Forwards and backwards. You can't do rotational conservation of energy without knowing V equals omega R. You can't really do Newton's laws and torques without knowing A equals alpha R. Those equations have to be jotted down somewhere. And like it or not, those are not on your reference tables. Those are ones you're going to have to be able to pull off of a resource, off of a cheat sheet, off of a Google search or whatever you're using. Those have to be the ones that you know pat on there. Okay. Other things that are useful to know but aren't on your reference tables is moment of inertia. Moment of inertia for a point mass, mr squared, not showing up on your reference table. Sorry, but useful to know. Pretty much any other moment of inertia question you're going to see will have I given to you. Although I'm really confident on this year's exam, you're just going to be able to see I be I. And they're going to talk about a generic object with this moment of inertia I and go from there, instead of having it be 2/3 mr squared or 1/2 mr squared or stuff like that. The gist with the moment of inertia, mass radius squared. In general, the more mass you have closer to the point that you are rotating about, the easier it is to rotate around. And the more mass you have far away from your center of rotation, the harder it is to rotate about it. Right? We then get into torques. Torques is Newton's law. The only difference is we're talking about rotating instead of linear motion. But it's still, just like F equals ma, torques equals I alpha. Anytime we talk about forces and we're rotating something, this is our go-to. Sum of torques equals I alpha. The unbalanced torques cause a rotation in our object. If there aren't any unbalanced torques, we don't see the rotation change, and we'll be in equilibrium. All right, Aaron says, what does a point mass mean? Okay, so a point mass would mean something that you can imagine existing in a single point. Like a human is not a point mass, right? All our mass is not in one single spot. It's all spread out. We are not a point mass. But a point mass would be something like if you were to look at a star in the sky, one of those stars that is so far away, it looks like a dot. We'll call that a point mass because it looks like a dot. It looks like a point. That sort of thing in there. Basically, that equation is useful. Not that you're going to calculate with it, but it shows us the relationship. It shows us that moment of inertia depends on m and depends on radius squared. If we have those two parts, we can put it together. More radius means bigger I. More mass means bigger I. Less radius means smaller I. Less mass means smaller I. That's the sort of relationship you're going to need to know about. Okay? So R in all of these bullet points is the radius, the distance from the point of rotation. So when we talk about any sort of things like this R in mr squared, or the R in S equals theta R, V equals omega R, stuff like that, that is the radius around our radius from our point of rotation. So showing in the picture here, if this is our point, radius would be our R value right there. Omega, alpha, theta, all those things are acting in the plane of the circle. So they're either going clockwise or counterclockwise. Whereas V, A, X, those things are on the arc tangent or pointing inwards and stuff like that. Okay, just want to point out with this picture specifically, this object has an acceleration that is not entirely pointing towards the center of the circle. Because it's not entirely pointing towards the center of the circle, the speed of that object will change. It will not be a constant velocity. The only time we get a constant velocity while we're going around a circle is if the acceleration is pointing towards the center. In this case, some component of this acceleration is pointing towards the center. There is some component you want to imagine is going towards the center here, and then some part of it is tangent to the circle. The tangent part is making our speed increase. The perpendicular part is making us move in a circle. And if you have both, we are accelerating in a circle. Okay. Other big points to point out here. Keeping a chart like this rotational linear sort of thing is not a bad idea. Even if it's just a shorthand that, hey, X is theta and V is omega and stuff like that going on there. And then we get our motion equations. Again, it's the same equations. All we're doing is changing our symbols. Wherever you see an X, you put a theta. Wherever you see a V, you put an omega. Wherever you see an A, you put an alpha, et cetera, et cetera, et cetera. Keeping in mind that these three equations are our link between the two types. A equals alpha R, V equals omega R, S equals theta R. Okay. For torque, let me get rid of my pointer here. So torque is going to be either clockwise or counterclockwise, depending on what it's going to do. So if we look at the wrench in the bottom left corner of this diagram, I can't draw on that because that's gotta, okay. The force is pointing downwards. It is downwards and perpendicular to my radius. So there is a perpendicular force acting on this, and that force, if you imagine, pulling down on that wrench is going to make it rotate in a clockwise direction. So the torque there would be clockwise. In the upper right wrench, same sort of thing. That force is not perfectly perpendicular, but there is some perpendicular component going on. That somewhat, or that partial perpendicular component is going to make that wrench, again, rotate in a clockwise direction. It just won't have as big a torque as the completely perpendicular one because some component of that force is going to make it rotate, not the entire part of it. And then the bottom wrench there, where the force is pointing towards the pivot, that has zero torque on it. You need to have a perpendicular relationship between the force and the radius. There is no perpendicular radius or perpendicular part there, so there is no torque. A nice example of this would be if you want to go into your bedroom or something like that and try to close the door. If you push on your door towards the frame, get on the skinny part of your door and try to push in on it, that will not move until you start pushing off to the side a little bit. The second you get some sort of perpendicular relationship, you will have a torque. Otherwise, it will not do it. Likewise, you can go to that same door and you can try to push on the hinge, right on the barrel hinges where that door connects to the wall. Try to push on that and see if you can get it to rotate. It'll be either very difficult or impossible to do because your radius is basically 0. And no radius means no torque as well. So for torque to happen, we need to have a force, we need to have a radius, a distance from our pivot, and they need to be perpendicular with each other. Okay, and I think I've got a question like that. Yeah, so let's do this question right now. I'm going to open up the poll again. So let's do the same sort of thing here. I'm just going to ask which one's the greatest right now. I got A, B, C, D, E, F. Okay, so which one's got the greatest torque? A, B, C, D, E, and F. What do we think? So with this, we need to be able to push. Oh yeah, so I'm changing the question, sorry. Which one needs the biggest force applied, F, in order to balance out this hanging mass? So we want to make this thing be able to balance and not rotate. Which one of those is going to require the biggest force applied to point F? All right, did I not create a poll? I thought I did. Can you guys see the poll? No, that's the same one there. All right, did that get turned off when I did? No, it should still be there. Interesting. I wonder if you guys can't see that poll because no one's answering. All right, well, if we can't see the poll, we're going to get rid of the poll then. And we'll go back to the other way of doing it. I love technology. It makes me so happy. So happy, so happy, so happy. Again, I apologize for the craptastic technology job here, but we do the best we can. Okay, so let's switch over here for a second. We will solve this question. All right, so we've got these 6 different options here. In every one of these cases, remember, torque is force times radius that is perpendicular. In this case, it doesn't look like we're changing any of the angles, right? This angle looks the same as that angle. So really, the perpendicular part isn't a big deal. All these are going to have some sort of perpendicular part going on. The other idea here is that we are changing the masses, force, and radius on there. So if we want the biggest force, that means that our pushing spot should be the closest possible to the point of rotation. So we want to be as close. We want to have our R be as small as possible to make the force be as big as possible. We also want to have the biggest possible torque hanging on the other side. So in this case, I am going to right away say A can't be the biggest, B can't be the biggest, and C can't be the biggest, because those 3 all have a hanging weight of 100 kilograms. D, E, and F have the same exact scenarios, but they have 200 kilograms. And 200 kilograms is a bigger force hanging, which means a bigger torque on the hanging part. So if I'm going to do this, let's just call this 200 RG. This is 200 2RG. This is 200 3RG. I'm just using R as one of these tick marks because They don't give us numbers, but basically this guy, F, has a 600 GR torque on it. The middle one would be a 400 GR, and then 200 GR. Middle one and E and F have bigger torques on them because the radius is bigger. It's the same weight, but it's further away. So the radius part of that, bigger radius means bigger torque. Okay. Now, the next part here, so I'm going to choose F so far has the biggest one, but let's look at where I'm pushing from. So I got to have 600 equal, or GR equals the force I have to push, F times R. Well, that means I need to push, well, I need to push 600 Gs over there. For C, I would need to push, well, that's 2 ticks over, so that's less. 1 tick over here, this one would be 100, so that these going to be like 300 in there. So basically, and I know this is tough to see on here, if we want to make the vertical force on there, the biggest force happens with letter F. It is the biggest hanging mass, which is the farthest away from the pivot, which makes the biggest torque in the counterclockwise direction, which means my force over a very short distance needs to be very large. Second most, probably going to be E on there. D is a lot easier than E because we're pushing from a farther radius away. That sort of thing. The smallest force we need, this would be the smallest, is A, because we have the smallest mass, the closest to it. This is a very small torque, and we are pulling from a very large radius on that side to make it go the other way through. Okay, let's do the next one here. I'm just going to leave it in here because switching back and forth doesn't seem to be very productive, and I want to maximize our time we have together here. So bear with me for a second here. Let's look at the second example. The second example is another rolling down one. Let's see what we've got here. So we have 2 objects released from rest. We have a solid sphere. Its mass is all evenly distributed towards the center and away from it. We have B and C, which are both blocks. They can't roll. And D is a hollow sphere. All right, here we want to rank the speed of the objects as they roll down the ramp or slide down the ramp and figure out which one gets to the bottom with the greatest speed. So who has the greatest speed when they reach the bottom of the ramp? All right, so in this case, I'm running through my checklist of things I can think about for this question. This is not a forces question. This is not a momentum question. This is not a kinematics question. This is an energy sort of question. Okay? This is an energy question where we can say, hey, all these blocks start with potential energy due to gravity. They all start with PEG. In fact, since they have the same height, they all have the same potential energy due to gravity. Right? Same mass, same height, same PEG. That PEG is going to get converted into kinetic energy for the objects as they roll down or slide down the ramp. There's no friction going on here, so we don't have to worry about energy losses due to friction or stuff like that. The problem is there are 2 kinds of kinetic energy. There's rotational kinetic energy, and there's translational kinetic energy. Rotational kinetic energy, 1/2 I omega squared and 1/2 mv squared. Now, what happens here? The bigger moment of inertia, or the bigger the fact that we are rolling here, what just happened? The bigger moment of inertia is saying that we are taking that energy and shoving more of the energy away from our linear motion, away from our translational, our sideways moving velocity, and shoving it into energy that is doing nothing more than making this ball spin. That is not making it move sideways. That is just having it stuck spinning on there. So the more energy we stick into KER, the less energy we have left over to be translational velocity. All right. Because we have a solid sphere and a hollow sphere, hollow, more of our masses are on the outside. Remember, I depends on M and R. In this case, we have a bigger R. We have more distance away from our center. So this has a larger moment of inertia, which means it is dropping more energy into making it spin and less energy into making it rotate. All right. And, oh, wonderful. Apparently Crowdcast is down, which is super appropriate for right now. That's wonderful. Hopefully that'll come up. If you guys are watching this later, that's what's going on right now is we don't have Crowdcast. So explanation for this, let's work out our reasoning here. So blocks B and C are going to reach the bottom with the fastest speed. All of their energy is all converted to translational kinetic energy, while A and D have some of that energy which reduces their translational kinetic energy. Yeah, good enough. There's a simple explanation there. We're not doing a ton with it. This is explain your reasoning. This is not BCDA. This is just simply talking about why'd you say that in there. So with that, there might be a case, though, for example, I think it's our next question on here. The next case where we are going to have a case where it is talking about rolling and which one goes further. But it's not the next one. We'll save that one for a second. There is one more I want to do first. And that is another classic one you guys may have seen already, but this is a good angular momentum question that I want to make sure we cover because I would be remiss without doing an angular momentum question with you guys since so many of you asked for angular momentum. So let me paste this one in to my bit paper. All right. So for this one, we've got a diver jumping off, and they're going through 3 stages. Okay, this is a clear, coherent paragraph length response, meaning we have to do our BCDA. That's our basic outline here with this. So we want to figure out why the athlete's angular speed increases and they rotate faster between figure 1 and figure 2, but decreases between figure 2 and figure 3. All right, scratch work off of the side here to begin with. Basic physics. Conservation of angular momentum. I think that's about it. L equals I omega. I depends on M and R. Okay, there's my basic physics part here. Now, why did I know we're talking about angular momentum? This sort of example, we're talking about rotating. We're talking about rotating faster. So there's really only 2 options that we can do when we talk about rotating and changing our rotation. We can do torques. We can see if there is an external force going on that's making somebody rotate faster. Or we can talk about momentum. And in this case, you could make a case that it's their internal muscles pulling in and stuff like that, making a torque, making them ball up and stuff like that. That works. That is not the easiest way to do it. but it is a viable option. Please don't let me say that that is not going to work. But this way is easier and more straightforward. Okay. Now let's see. Do we have stuff back up here? I'm not sure. Well, possibly. I just got a notification that Crowdcast came back up. So hopefully it's back up. So there's that site evidence. We're supposed to say figure 1. The person is spread out. Actually, I can say figure 1 and 3, right? They're basically the same thing. Figure 1 and 3, the person's spread out and they have a lot of their mass far away from the rotation point. Figure 2, they're tucked in. And then I guess we already have our A already. We're supposed to say that so that's our answer. They kind of told that, which means we really don't need to talk about it in the paragraph part, but I'm going to put it in because it never hurts just to get to that clear, concise answer part in there. All right, so our description, this is kind of where we're going here. So yeah, all right, I'm going to mark that as done. Let me start a new tab to write on here now and actually write out this paragraph here. Since there are no external so that's kind of my paragraph for this here. Well, that kind of didn't enter on there. So looking at something like this, we kind of hit our key points here. looking through the parts, conservation of momentum, defined L, I and omega, told what I depended on. You could put here I equals mr squared. That's fine. It's not perfect because this person isn't the point, but it gets the gist across, and that's what we're looking for in this question. You understand that a bigger R means a bigger I, and a smaller R means a smaller I. So there's an example of that FRQ part. I would strongly encourage you guys, when it comes time to write these, when you're going through it and jotting stuff down, kind of do what I did off to the side here. Make a list. Talk about what you have going on before you sit down to actually write it. Do not just dive right in and try to just power through these questions. Take that 30 seconds, take that minute, 2 minutes, whatever, and get a clear plan for how you're going to go about solving and writing these prompts. Because it is very easy. If you just sit down to start writing, you will miss a key step. You'll miss your C, or you'll miss your B, or you'll miss some key physics concept in there. So please take the time to sit down and actually plan out your writing before you write it. Just like you would for an essay in English or some other global or social studies class or something like that. Plan before you write. You've got enough time to do that. And it's going to make the writing part go a bit quicker too. Okay. Also, again, don't be afraid. If you're going to put equations in, put equations in. L equals I omega, that sort of stuff like that. We like to see them. They're going to work. And then as long as you've got it typed out and clearly said what you're going to do, you're fine. As Christian mentioned, probably not going to have Greek letters. Although if you do, like I use W instead of omega. I think we're going to be on to understand what W means when it's supposed to be omega. That sort of stuff. So keep that in mind too. All right. Then, kind of already did that one. Oh, let's do this one. This is the last part here. This is our last rotation one. Then we'll go over some of the other FRQs and stuff like that, and kind of hit general concepts, general trends, tips, that sort of stuff like that. So let's pretend this was from another longer FRQ. I just stole the last part here because I wanted to spend some time talking about torques again, because again, that's a very popular topic for us to cover here. So we've got a pendulum swinging back and forth. And the question tells us that as this pendulum swings back and forth, there must be some change in its rotation, where it goes from rotating clockwise in this case. So in case one, when we're moving to the left, we're going to rotate in a clockwise direction. And when we swing to the right, we're going to be rotating in a counterclockwise direction. In order for the sphere's rotation to change direction, a torque must be exerted on the sphere. So there must be a torque in order to change its rotation. Makes sense. Just like we have to have a net force to change our linear motion, we have to have a net torque to change our rotational motion. And if we don't, we won't have a change in motion. Okay? When the sphere is at its maximum rightward displacement, so when we are all the way to the right, when we are at this final point, right over here, what is the direction of the torque exerted on the sphere with respect to the point of attachment? Briefly state why. Okay, so we can do this a couple different ways. I'm going to do the cheesy way first here, and by all means, do the cheesy way because that'll work just as well as the long, complicated way. But let's start with the cheesy way here. I can say that torque has to be the thing that's causing us to change direction. Counterclockwise, clockwise. So we are rotating in a counterclockwise direction. And then in the next instant of time, we need to be rotating in a clockwise direction, which means the torque needs to be also going in that clockwise direction. Just like when we're talking about accelerations and forces, whichever direction you're accelerating in, there must be a net force in that direction. The same thing applies with torques. Whichever direction you are changing your rotation in, so in this case, we're changing our direction into the clockwise direction, our torque must be going in that same direction. And that's perfect. That's all we really need to do for that question. Now, because some of you are going to ask, let's draw a picture of the ball again, and let's talk about why. From the point of attachment, so there's my bob, there's my attachment point there. Why is that torque going in the clockwise direction? Okay, so in this case, this torque, there's a tension right there, acts a distance r away from our pivot. So all good there. Tension in r. This part has a force going down and a force going over. Okay, breaking up that into its components. Downward force, horizontal force, makes sense there. Now, only the horizontal force can cause a torque. So only this guy right here can make a torque. The vertical one can't, because the vertical one would be going straight through the radius, and that's down there. That's not perpendicular. So it has to be the sideways one. And the sideways one, what's it going to do? If I follow that arrow around, it's going to want to make this thing rotate in a clockwise direction. So you could also say, continuing along this, the horizontal of the tension, the force that causes the torque, is pointing towards the right. I want to call this the sphere. Yep. There's the second part there. So either way you can do it. You can just talk about very generic, very general, or you can get a little more specific. For this question, I like the first example a bit better. Just simply saying, hey, we're changing from one direction to another, therefore it's got to be going in that sort of direction. But the other one's perfectly fine too. Both will get you full credit. And the keyword here is briefly. We're not trying to write a book on this, right? Briefly state, one sentence. Keep it short, keep it sweet, get through the parts that you need to here. Also, just to point out, this was part K on this FRQ. And I'm sure a bunch of you guys have seen this question before. But what that means is they're not expecting you for this type of question to write a ton of information. They want you to get in, answer the question completely, thoroughly, show you know what's going on, and then get out. Don't write a book. Okay? When it says paragraph length response, when it says justify your answer, then write a lot more, but keep it short when it says brief. Okay. All right. Then, all right, we got about half an hour left. So what I want to do next then, I think, is let's talk about some tips. And then I'm actually going to, if you guys could, Aaron or Jake, can you turn the chat back on? I just want to know topic-wise. I know we've covered a lot of stuff already today. Is there one topic that you guys want to spend more time on in the next half an hour after I'm done with test taking tips and stuff like that? So if we can get the chat turned back on, and then I'll just plan for that last chunk. And if not, I'll find something else to cover as well there. But all right, so let me stop sharing this, switch back to the slides for a second. So when you guys ponder that, what topic do you want to have for our last little chunk of time while I'm getting set up to do the test tips? Okay. Yeah. Let's see, where am I here? All right, so tips for you guys. Okay, writing tips. This is kind of, I know Christian started the night with it. I'm kind of wrapping up the end with it here. Always, when you're writing out a response in paragraph length form or one that says justify your answers and stuff like that, stick to making sure you hit BCDA, CBDA, something in that format, that you've got evidence from the problem, that you've talked about a basic physics concept, that you've talked about forces or conservation of energy or Newton's laws or conservation of momentum or some equation off the reference table. Some basic physics thing needs to be in your response. Okay. You also need to pull in the evidence from the question, the important evidence. I don't care that we're ignoring air resistance. We never care about air resistance. I don't care, for example, in that last question we did about the fact that pendulum is converting potential to kinetic. It didn't apply to the question. So pull in the relevant information, relevant physics equations, draw them together, describe, define, whatever other D word you want to think of that means say why they're important and how they relate to each other. Do that part, and then answer the question if you need to. If you're used to writing in a CER, claim evidence reasoning format, that works perfectly fine too. Just make sure you get in your evidence some of that basic physics stuff as well. Okay. Other tips, as a reader, stick with one approach. Please do not try to mix and match halfway through. Don't start your argument by talking about forces, then suddenly jump to talking about energy, and then end up somewhere way over here where you're talking about rotation and torques and stuff like that. That's why I encourage you guys, plan this out before you start writing. Make your list, make your CBDA, jot it down as you go, so that when we get to the point where we need to put it all together, we can hit this in a clear, concise, well-organized paragraph. Okay. Other things, correct physics is important. Don't tell us something false, which kind of is a dumb question, or a dumb statement. But basically, the two ways you're going to lose points for these things are either you're not going to tell us some key physics part, or you're going to wander off topic and tell us some logical part that's wrong. So yeah, correct physics is important. It's kind of a duh, but it's just a reminder, we should have physics in your answer. It's a physics test, not a writing test. As much as we're going to be writing this year, you still need to have the correct physical relationships and describe them properly. Direct, indirect, squared relationship, numerator, that sort of stuff like that needs to be in there. But starting out with, hey, the equation for finding the acceleration is A equals F net over M, Newton's second law, is a really good physics thing to put in. That sort of stuff like that. Don't wander, stay focused. I know we've had a couple of discussions already in the chat and in the comments about, well, what do I do? Do I type? Do I post? Do I handwrite? Do I photo? The College Board accepts all of them. Looking at the problems or the issues that Physics C had on Monday, most of those issues were with kids trying to upload pictures and either ran out of time or had some sort of technical issue. Very few of the kids who had problems were actually copy pasting their answers. So as Christian said, I'm going to strongly encourage that you type out your answers. Okay. Type them out, get comfortable with the Google Doc, copy paste, Control A, Control C, Control V. Control A grabs everything. If you didn't know that already, nice, easy shortcut. Control C for copy, go over to your exam window, Control V, paste it in, and then you're good. This does mean no big derivations or long equations. And if you do have to write down an equation, write it out as best you can using the keyboard. Caret for squared, slash for divide, parentheses, and I don't know, SQRT for square root or something like that. You can type out all these equations in the text, and that's fine. Now, if you are the handwriting type person, you've handwritten all your answers so far this year, I don't want to change you. If you're comfortable with it and you can get it done quickly and easily, do it. Don't go crazy with that. But I will say, make sure you're giving yourself enough time then to make sure that you can take a picture, you can save it in the right format. If you're an iPhone user, College Board has some steps on how you can save your picture as a JPEG, because the default format for an iPhone does not work when you're uploading it as a picture. So save it in the correct format, get it over to the computer, and then get it uploaded. Make sure you save yourself enough time for that. I'd hate to see you lose points or lose the exam and have to retake it in June because you had your Wi-Fi drop out all of a sudden, or the AirDrop didn't work, or something like that. So if you're going to do photos, give yourself time for it. I strongly recommend you type, but if you're going to do something else, go for that. All right. Last second tips, maybe last 20-minute tips. Think before you write. Okay. Plan out something before you just start putting pen to paper or fingers to keyboard. You've got scrap paper off to the side. I'd recommend having a couple pages, even jotting down over your reference tables and stuff like that. These are the important things for this question. Speaking of that, when I teach my kids to do this, we try to break our question into certain topics. So if this was a full year, they'd have like 6 or 7 different topics. Is this forces? Is this energy? Is this rolling? Is this a spring? Is this a pendulum? That sort of stuff like that to help us narrow our focus down so we are focused on the appropriate, correct information for that question. And we're not getting off topic and distracted and stuff like that. The other part with that, derivations are useful. Even if you don't actually end up putting it in your response, having an equation that is solved for the final velocity of a collision and momentum, where you can say clearly, oh, if you increase the mass of the first thing, you'll get a bigger V at the end because here's this relationship. That helps highlight it, even if you never end up putting that equation in your final response. So jotting stuff down to the side may be really good. Okay. Again, don't wait till the last minute to submit, and don't stress out. A lot of the stuff that you guys can see, a lot of times people fail is not because they don't know what they're doing. They will fail because they are freaked out and stuff like that on there. Okay. Thanks. A lot of requests for Unit 3. Okay, we'll do some circular motion. Stuff like that. You guys can do it. You've studied. You're taking this time now to cram in as much information as possible. Tomorrow, you can do some more review. You can get your study guides put out. You can get your reference table set up. And that way on Thursday, you are just ready to go. You can do this. Each one of you has the capability to do awesome on this exam. Focus on it. Don't stress out. And just be ready for that game plan. All right, you guys can do this. It'll be awesome. All right, so request for Unit 3 overview. So Unit 3 is circular motion. So let's see if I can find some circular motion stuff going on here. You know what? This one's kind of a circular motion question. It's a bit overdone. Like I probably have used this particular slide in a good 3 or 4 different CRAM sessions, but hey, let's do it. We got time. Let's do circular motion. Okay, so circular motion. Let me snip this first and steal it for my stuff. So I'm going to switch back to the Sketchpad here because I don't have a nice, easy UCM cheat sheet made up already. Okay, stop presenting. Go away. Okay. Now, sorry about this. Give me another 5 seconds to get over here. We'll do an overview. We'll do that pressed question, and that should probably take us pretty close to the end of our time.